Good day all and welcome back. Welcome back. So like I said, okay, we're going to start it off with 12. Sorry that the break wasn't as long as yesterday, but it's just there's a bit for us to get through. Before I actually go on, I just rechecked this now within the break, and we actually saw that there was a thing that there was a sign that I changed when I went from one slide to another slide. So if everyone can still see my slides, if you look over here, when we multiplied all of these together, right, so if everyone check over there, you'll be able to see that I have this -4. Yeah, right. So we have this -4 multiplied by -4, which was this over here. Okay, was positive 16. But when I rewrote it on the other side, because I was speaking and things like that as well, there was -16. So then, therefore, my final answer was different to what I initially had on my pages over here. So eventually what's supposed to have happened was then this was not supposed to be 416. As you can even see, I was a bit confused during my lesson. I was like, oh, I know I'd done this right earlier. So this was actually 384. And if we place 384, -384, where it's supposed to be, which was this over here, -384, the answers that you should actually get for these two, one will be in fraction form, we'll just write it as 24/7. And on this side, we'll write it as -4/3. So everything else is the exact same. That's just on this side, then you will say it is now -4/3. And this is going to be 24/7. So then this should come out. And then this value will be instead placed on the side. And this value will be placed on the side. So sorry about that, guys. It was a bit like this risky run of carrying things over from one slide to the other side. Sometimes mistakes happen. So unfortunately, this was quite a bit because just I left my minus to a positive. So everyone else also, please always just check what you have as well when you are carrying over from one slide to the next. Now, let's move on to the next question. And the next question is going to be all about question 5. And question 5 is trigonometry. Now, the way we're going to speak about trigonometry is here, it says sine 40 degrees is equal to P. Write each of the following in terms of P. Right, so here initially you see we have this sine 220 degrees. Now, if we think about it this way, we know sine is usually opposite over hypotenuse. And here they're telling us sine 40 degrees, only sine theta, sorry, sine theta is equal to opposite of hypotenuse. But here they're telling us sine 40 is equal to P. But that actually means it's over 1. So if we write that down, let's make it like a Cartesian plane over here. So then we'll go up like this, this. So in this particular case, we're dealing with 40. We have our 90 degree over here. And then that means sine 40 is equal to opposite over hypotenuse. So opposite our angle, so it's the side over here, that will be P. And our hypotenuse is at the bottom, so that will be 1. Right, so we have it just like this. Now, we don't have our equation in our first quadrant where it is dealing with an acute angle. Instead, this is dealing with 220. So where do we find 220? We know this is 0 or 360 degrees. This will be 90, 180, and 270. So it will be inside of our third quadrant. And in order to usually calculate using your reductions in the third quadrant, will usually be 180 minus your theta. So that's how we're going to get it inside of here. So before we can do that, we need to find out what is our value here at the bottom. So let's say, for instance, maybe let's just make this as our x value in this triangle. So if we do it that way, can we actually solve for that side But of course, as a 90 degree, and we know two sides. Whenever we see that, we know we deal with Pythagoras. So you can just say r squared is equal to, that's going to be my hypotenuse. So r squared is equal to my x value, which is x squared, plus my y squared. So if I plug that in, it's actually going to be 1 squared is equal to my x squared plus my y. And my y is going to be p, right? P squared. So I have it like that. And now we're going to square all of this. So 1 squared is still 1. All right, we're going to leave that as x squared plus p squared. All right, so we should have that over there. And then now what we're going to do is we're going to bring x squared on its own, because that's exactly what we want to calculate. So that's going to be x squared is equal to your 1 minus your p squared. And then we're just going to square root these. So that means our x is going to be our 1 minus p, right? So it's going to be just like this. So that's going to be our x value. So x is actually going to be 1 minus p squared. So if we take this eraser over here, so now we all know that's 1 minus p. Go back. 1 minus p squared. This is square root of the entire section. Okay, now that we know our three sides that we have for our angles, what we could now do is we could now try and find the missing angle within here as well. So we find all the sides, and now we can find all the angles in this angle or in this triangle. Let's make a, I think I can try and throw it over here. Here we see we have it as, if I have a triangle here, 90, 40, and then this, of course, going to be those two minus each other. So let's maybe just say that maybe is beta, right? To make it as beta. So in order to calculate now the angle within there, we know the sum of the triangles. So that's going to be 40 degrees plus 90 degrees plus our angle beta is all going to be equal to 180 degrees. And why is that? That's because of the sum of the triangles always equal to 180 degrees. So we make beta the substitute of the formula. Beta is equal to 180 minus 40 minus 90. And if we type all of that in a calculator, we'll see that beta is equal to 50 degrees. Right now we know, okay, that is 50 degrees. So let's erase at least the spot here. So don't erase all the important information, just know that beta is 50. So we take that away. Right, so that's this, and we're going to take this part away. We know that's 50. Our pen and 50. Now, this is going to be the part that we're going to try and focus on through everything, and just to make sure that we know everything now. So that's 1 p and 1 minus b. Okay, so this is the main angle that we have. So they want to know sine of 220. So if that's the case, where do we find it? Inside of quadrant 3. How do we go from 180? What's the difference between 180 and 220? That's going to be 40. So we're going to write it as our reduction formula. So instead, we'll write it now as sine 220 degrees. That's a 2 and not a 7. We're going to say that is equal to our sine of 180 minus, say that is 40. Or to get from, oh, sorry, plus. Sorry about that. This is going to be plus because over here also was plus. Because, yes, sorry about that. I was minusing the 180 from the 220 made. But anyway, 180 plus 40 will give us sine. Will give us this, right? But what is sine within that particular quadrant? Well, if we go over here, by now you all should be familiar with the diagram cast. So it's in number 3. So it's in this one over here. So therefore, this is going to be equal to negative sine of 40. right? So now we made it an acute angle, right? And now negative sine of 40. So if we look at that, what is negative sine of 40? Well, we already know what sine of 40 is. Sine of 40 is equal to P, but we should not forget our negative. So we write sine of 40 is equal to P, so that is P. And we do not forget the negative because it comes down over there. And because this is dealing with high sine, remember it is negative P over 1. But that's our answer. So your final answer here is going to be sine of 220 degrees is equal to negative P. There we go. And that's how we answer 5.1.1. Perfect. Now, moving on. 5.1.2, cos squared 50. How do we write this in terms of 50? Sorry, in terms of P. We're going to be dealing with this again. This is our template that we're going to be focusing on. All right, so that's a template. So make sure everyone else write that down as well. You have that because that's what we're going to relate all of this to, because all of this is dealing with 5.1. Right? This was 5.1.1. This is now 5.1.2. Now, whenever you see cos squared 50, remember that is the same as cos 50 squared, right? That does mean the exact same thing. So just make sure you follow along with that as well. Now, for those that didn't write it down, let me write it down again so everyone can follow along. So remember, this was our 1 minus P, this was our P, and this was our 1, 40, 50, 90. Right, so we have it like this. Now, there we can already see, perfect. We have a 50 year and we have a 50 year. We know when it comes to cos, it's always adjacent over hypotenuse. And we remember that with SOHCAHTOA. So we know it's adjacent over hypotenuse. So what is adjacent of this 50? Adjacent would be next to it. So it's this side over here. So that is going to be our cos squared 50. All right, so it's basically that is equal to our P, which is our adjacent, all over our hypotenuse. What's the hypotenuse? It's always opposite the 90 degrees, so it's 1. So it's that over there. But this is squared. So in that particular case, we're going to deal with it like this. So we have it as adjacent of hypotenuse. So therefore, we're going to say that this is going to be this squared, right? And then your answer is going to be cos of 50, right, is equal to, you square that, and that's going to be P squared. Right, so that's how we write it in terms of our, or at least we write it like how they had it at the beginning. So here it is. The reason why we're squaring it is because we have the square over there. So always write it like they say in terms of what they're given. So cos squared 50 degrees is equal to P squared. There we go. Perfect. I see that you guys wrote it down already. Perfect. So that's it. Okay, moving on to the last one when it, oh no, I think, yes, the last one when it comes to this 5.1 section. Now we see this is cos of negative 80 degrees, and that's worth 3 marks. So don't worry, I will give you guys time to also, answer some questions, but we'll get through when it's more difficult ones. All right. Yes. So, okay. Now, when it comes to negative 80, that is clearly not on our cost diagram. Because remember, like I showed you, 0, 90, 180, and 270. So here we don't see any negative. But what we can do is we can always add it by 360 degrees. And the reason why we can add 360 degrees, or maybe minus if it is more than 360, because remember your cost diagram just deals with 360. If it is more than 360, you can always minus by 360. If it is a negative number, which is less than 0, you can always add it by 360. The reason for that is you will have a point on the graph. Let's say, for instance, that is negative 80, like we have over here. Then all that's going to happen is we are going to increase it by another 360 degrees. And remember, that's the entire revolution. So you'll start where your initial part was. So all we do here is we say cos of negative 80 plus 360 degrees, right? And that is now going to be, so we can write it out, cos of negative 80 plus 360 degrees. That's going to give us an answer of cos 280 degrees. Now, in which quadrant do you find that? This time, it's in quadrant 4. And what is the reduction formula within quadrant 4? That's going to be 360 minus theta. So here we write that down. So cos, in brackets, your 360 minus, what will give us that difference now? In order to get from 280 to 360, that would be 80 degrees. So that's the same as that. And then we look, okay, what is cos in that quadrant? Well, it's positive. But remember cos diagram, C-A-S-T. It is found in here. So therefore, it's positive cos 80. Right? And there we go. So this is not yet in terms of P, because that's what we want. We want all of our values now to be in terms of P, right? So instead, what we're now going to do is we are going to see that this, if we have our angles over here, if we look at our triangle that we have made, we have a 90 degrees, we have a 40 degrees, and we have a 50 degrees. But they are speaking about cos of 80 degrees. So when we speak of now cos of 80 degrees like this, that actually means now we're going to deal with our double angles, right? Compound angles. And this is how it's going to be run. We can now say that this instead could be written as our cos of 2 times 40. Right? So see, now that is within our triangle. This over here. Right? One of that is within our triangle. Now, when it comes to compound angles, just to make sure that everyone is on the same page as well. So when it comes to compound angles, as an example, this is the general formula that follows. Cos of 2a is equal to, it could be one of three things. Formula sheet, this is my just big squiggle brackets. So it could be cos squared a minus sine squared a. Like I said, this is on your formula sheet, but just moving along so everyone can follow along. Or it could be 2 cos squared a minus 1. Or the final one could be 1 minus 2 sine squared a. Now, out of these three, which one should I use to find that part? Well, we don't know about cos yet. So you are correct. I saw in the chat as well, someone said it. We're going to use this. Why are we going to use this? Because we already know. Yeah, we can already see we have an answer for what sine is already. So let's use the one that has sine within it. So if we're going to do it that way, we will then say, now this cos of 2, which of my, this is basically, remember that 2 is this 2. And then my a is 40. Right? Just so that everyone knows as well. Now we're going to plug it into this formula. So we're going to say 1 minus 2 sine squared. And what was the angle? 40 degrees. And then we are going to now sort that out. We said that 1 minus 2 sine 40 is the same like this, right? Sine squared 40 is the same as sine 40 squared, right? So we have it like that. So in that particular case, we're going to write it again. 1 minus 2. What was our sine 40? Remember, it was given over here. So we know that is actually P over 1 squared. So then we're going to square this over here. So as you can see, this is divided by 1. So what you could then just say is this is equal to 1 minus 2p squared. And that is our answer. But no, I first need to write this as well. Because remember, always write it how they asked it from you. So we actually say cos negative 80 degrees is equal to that. And that's how we had it. All right, so I hope everyone got that as well. Was 240? Yes. Okay, I see everyone done that as well. Okay, perfect. And that was this part done. All right, so that was a nice 3, 2, and another 2 marks over there for you. All right, nice and easy. Yeah, it comes to the identities. And this is usually the part that usually catches some people out, but we're going to try these identities. Now, there are different ways to do this identity. And they say usually look at the most complex version in order to deal with these identities. And there is different ways to do this. And I actually have done both methods for you. So what I'm rather going to do is I can actually just show you both sides or both ways, and then we can carry on with this, right? Because I mean, there's no use I tell you do this because eventually you must get to the right answer. Now, let's say, for instance, if we choose the left-hand side. Now, I know the more complex side is the right-hand side because we see it's a fraction and it has everything else. I want to show you it is doable when doing both. All right? Is everyone okay with me doing that? Let me rather just get a diplomatic response because I know this is going to be a long section. Do you want me to show you both sides or do you just want me to show you the right-hand side and then the left and then we move on? Okay. Okay. So let me show you what we have over here. So thank you for answering. So, okay, we're going to choose the left-hand side. What is the left-hand side? We are going to say this is the left-hand side here. So tan x, which is 1 minus cos squared x plus cos squared x. That needs to eventually equal to our other side that we have. Remember, you are by all means welcome to do this as well. The first identity we can see is tan x. We know tan x can be written as sine x over cos x. Right? The rest can say the same. 1 minus cos squared x. And we can leave the other cos squared x there. Cos squared x. We're eventually going to move it around, but at least I just want everyone to see that in the meantime. Now, these can be multiplied with each other. So this top section can be multiplied here, and the bottom section can be multiplied with that. So that means we can write it out now as sine x, and then in brackets, that will be 1 minus our cos squared x, and all of that is divided by our cos. So that is going to be our cos, this is supposed to be x here, cos of x, and that's plus cos squared x. Now, by that, everyone should already have seen, even like before I wrote cos squared x already down, you guys should have remembered that you have sine squared x plus cos squared x is equal to 1, which means we could also write it out as cos squared x is equal to 1 minus sine squared x. So that's what we're going to do over here. We're going to write it as 1 minus sine squared x. Remember, you can say if I'm going too fast or too slow, but I hope everyone is along with me so far. Now we see there's a plus in between both of these. So when it comes like this, we could actually just say this is over 1 as well. Now we have fractions that we're going to add. And whenever you're going to add fractions, you are going to multiply your denominators together, and then you take the denominator of the one and you multiply by the numerator of the other one, and the denominator of the other one, and you multiply by the numerator of the other one. So that 1 multiplied by cos x is just going to be our denominator as this. Then we are going to have it now as we have our sine x. So we just write this usually down. With 1 times that initial concept is still 1 times cos minus, 1 minus cos squared x. All right. And that's going to be plus. We're just showing that this is going to be how we get to that as cos x multiplied by all of it that we have, 1 minus sine squared x. So we're going to multiply this in here as well. So that's going to now be equal to, if we multiply this in, this is going to multiply here, and this is going to multiply by that. So that is sine of x minus sine x times cos squared x. Plus, now these are going to be multiplied as well, and those are multiplied as well. that is cos x, cos sign negative, cos x times sine squared x. Remember, you could write that either way. You could write as minus sine squared x times cos x, right? So we have it just like that. And that's not all, because all of this is still over our cos of x. Now, when you look at it this way, now you need to factorize the things that you have. Different things over here. We have our sine x, and we have another, there was a minus sine x over here. Yes, that's fine. We have our cos squared x, and we have our cos and the sine squared x. Okay, so let's see if we can actually multiply all of this out together, right? So I'm just making sure we have everything together. So that's sine and sine squared x. Yes, that's all together, and that's all together. Okay, so we're going to put all of this together now, and I'm going to move on to the next slide. So I hope everyone still has a spot over here. Now, when we're going to rewrite the next part, we're going to say that is now equal to our sine x plus cos x, and that's minus our sine x times our cos squared x minus our cos x times sine squared x all over cos x. Now we take this part out. We can put these together. So we can say this is now instead sine x plus cos x. Right, we put that together and minus it by our sine x times our cos x. And then if we put this in brackets, now we can say, because if we took this out, if we put a cos x here, a negative times a positive is a positive, and then we're going to have it as a sine x here, all over cos of x. The reason why I got that is because, look, this is one term here. Here is one side, here is the other side. If we took this out as a common factor, sine x multiplied by cos x, or yes, and then that multiplied by, and this over here will give you sine x times cos x squared, which is this on top, and then then you're going to say negative times positive is going to be that other one on that side. Right? So everyone's still okay? Everyone's still following along? Now that we have it, hey, look what we have. This, even though this is written with sine first, here we have sine at the back, here we have cos second, but here's cos is in front. Because we are adding, it does not matter. It could swap around. 2 plus 1 is equal to 3, and 3 plus 2 is still equal to 3. So we can, of course, swap it around. So that's our common factor that we have. So now that we have a common factor, we take all of that out. So we now can say that is sine x plus cos of x. And that's going to be our 1 minus sine x times cos x all over cos of x. And now if you look over here, what do we have? Well, we have our identity, right? So that's 1 minus, there we go. And that is our part over there, just like that. Yes, guys, you know, I misspoke. I was trying to just focus on there. That was an example at the top of my head. But anyway, yes, there we go. So then you state left-hand side equal to right-hand side. Now, everyone got that? So may you please repeat how you got to sine x plus cos x in line 1. In this particular one over here, I think you mean? Oh, sine x plus cos x, you mean that section over here. Here we're going to say this part. I moved it around. This was my sine x that I had. And then instead of just writing it like usual, when you have a plus, you are allowed to move things around. And then I put that there. And if you see here, it's still the minus sine x times cos x squared. If I move over, I didn't get rid of that. It is still minus sine x. So it's almost like you took this as a full section and full section. Pleasure, guys. Okay, now moving on to the right-hand part of this. So this one is going to be what most of the people would actually try out, but I wanted to show you the other way is possible as well. So this is what we initially have. Writing too high on here. Okay, there we go. This one. So let's write that. Sine x plus cos of x. And that's 1 minus sine x times cos x all over cos x. All right, so we have it like this. Now, we have two brackets, and the first thing we can do now is we can multiply these terms with each other. So you're going to take this and multiply over and over. So before we do cos, we'll just do this one over here. So that is going to be sine x, and then sine x times sine x, that part over there. So that's going to be positive times negative is a negative. Yep. Sine squared x times cos x. And now we do the bottom. It's going to be this. So that is going to be positive times positive is positive cos x. Positive times a negative is a negative sine x times cos squared x all over cos of x, right? Never forget to always put your all over section. Now, do you see that this cos is divided by everything over there? And that's very important because we could actually rewrite it now. We can now instead say sine x divided by cos x, and then you take your sine that you already have, and then you just get on sine squared x divided by cos x. All right. Oh yeah, sorry. And then you add that as well because it's still one term, cos x. You put that over there, and then you add your next term, so that is the plus now, and that came from here. And then there's going to be cos x all over cos x as well. And then you put your minus, got it from here, of course. So that is sine x times cos squared x all over cos of x. There we go. Now that we have it like this, here we can see that in this particular case, sine x over cos x, we know it's a trig identity, which becomes tan x. In this next section over here, let's just make that line a bit more solid so you can see. This can be cancelled with this one over here. So that now just becomes sine squared x. There we go, plus cos divided by cos is just 1 minus, in this case, we have this that can go together. So here we see we have this that can go together as a trig identity. So we can actually rewrite that. So we have a minus, and we say tan x times cos squared x. Everyone still following along? Everyone okay? You can give thumbs up, thumbs down. Everyone still okay? All right, so this is what we have. We're still not there by our other side yet, but at least we have all of this. All right, now what we're then going to do is we are now going to group all the parts that we can see together. So in this particular case, here you see we have our tan x on the side. So everyone have this particular section, all right? So now here we see here is a tan x on the side, and here's a tan x on the side. All right, I'm going to move over to the next page, but I'm pretty sure everyone followed along. But all I'm going to do now is I'll tell you what I'm going to do before I write it in. I'm going to take this. I'm going to put it next to my other tan x. I'm going to take so that entire section, which is this whole part here, will be rather written next to my tan x. Then I'm just left with the other two next to each other. As you can see, this is a positive 1 that I have over here. So we can move around that freely. And this ends up with being minus sine squared x. So now all I'm doing is moving things around. So this is how it's going to look, equal to tan x minus tan x squared times our cos squared x plus 1, just to make it a bit easier. Then we end off with our sine squared x. So we have it like this. And hey, if we look at this, now we can see the reason why we swapped it around is because here we have a common factor. 1, here's a tan x here and a tan x here. So that can now be equal to, we take that out, tan x, 1 minus cos squared x, close our bracket, and this is now going to be plus, but hey, don't this look familiar as well? I'm pretty sure it does. If everyone remember over here, it could be the same as this what we have here when we rearrange it. right? So instead of having now, we can rewrite it as cos squared x. Oh, yes, I already have it here. Let's use it there already. Cos squared x is equal to 1 minus sine squared x. And then we go back over. There you see that's 1 minus sine squared x. So that just becomes cos squared x. Right? So we have it like this. And that is everything. See, that is that. So therefore, right-hand side is equal to left-hand side. And that's how we do this trig identity. Okay, that was a bit of a long one, but I hope everyone understand. And as you can see, trig identities is just a few that you at least need to remember. And when you see you can't do anything else, or you get confused, rather start grouping things together. And then from there, you can try and find new things as well. Perfect. Now, moving on. 5.2. For which value of x in the interval, x is the element of negative 180 and 180, will the identity be undefined? So, for which value of x will that happen? So here we see, easy way to think about this is that x. They're speaking about x, and these x is everywhere over here. But what I feel like saying is that if we manage to make this entire part over here, so now that's x, where they're asking which value of it will make it undefined. Do you agree if I say, if cos of x is equal to 0, this will be undefined? Because we can't have any fraction or any number divided by 0. It will be undefined. Even if you try it now on a calculator, you'll see you'll get an error. So if we make cos of x equals 0, then that means we'll be able to find out that this those are the values that will make x undefined. Now, you can't just write if cos is equal to 0, it will be undefined, because that's not the final answer or what they want. So what you need to do is you need to see what values, what will make x equal 0. And the way you do that is by using cos x equals 0, and you make x the subject of the formula. So that is cos like this of 0. If you type that in your calculator, you'll get 90. Now, don't just write 90, because 90 is 90 is, that will actually give you a 0 eventually, but this is actually going to be, your answer have to be plus or minus. And the reason why I say that is because if you have cos of 90, it will equal 0, and if you have cos of negative 90, will also be equal to 0. So therefore, which values of x, they even kind of gave you a clue there, it's plural, which values of x in the interval will give you this, is going to be when it's cos of 90 and cos of negative 90. Right? So this is how it's going to be over there. Yes. So when we have it like this. So when x is 90. Yes, that's correct. When x is 90. Okay. So now moving on to my next one. So see, that was just worth 3 marks. That's not as much writing as all of the other things that we've been doing recently, because they've been saving it for at least a year. Right? So this one is now going to be a 6-mark question. It's going to be a very long question. I think now that was a lot of talking that I've done so far. I would like you guys to try this out right now. I'll give you, say, 6 minutes. So, sorry, 6 marks. So it's worth 6 minutes. All you have to do is you need to now look at this. And I don't have to give you any extra information. Just without the use of calculator, you need to say and simplify the expression given above to a single trigonometric term in terms of cos 2x is equal to something. So basically what we're telling you now is, in the answer you're giving me, you're going to have cos 2x. But it might be cos 2x plus something, cos 2x minus something. It might be cos 2x divided by something, or cos 2x. Yeah, or either the cos 2x is going to be on top in the numerator or in the denominator, or it's going to be added or subtracted. Let's see. So I'll give you 6 minutes. Starting now. Okay, so welcome back, everyone. I hope that everyone have tried out the answers. I don't know if I came back a bit early, but I'm not seeing any answers over here. Anyway, I'll start working out, and then hopefully you guys will have the answer before I get to my answer as well. So now, just make sure I don't write with the actual pen. So, okay, the first thing we're going to do is, this is what we are given. And they say without the use of a calculator. This is our given expression. Based on that, the first thing we need to then do is, we need to make this into an acute angle. So that means, of course, make it to less than 90. So how do we do that? We go to our diagram that we can make. So 150 would be not here, but in between here. That is 1, 2. All right, in your second quadrant. And then that means it's going to be 180 minus theta. So here we go. We're now going to say that is now going to be equal to our sine of 180 minus theta, and 150 plus 30 is going to, of course, give us our to get to 180. So that's going to be 180 minus t. Right, we have write like that, plus our cos squared x minus 1. All of this is divided by 2. Right, so we have it like that. Now, is sine positive in this particular section? Yes. Once again, cos. C-A-S-T. It is positive. So there we write it as positive. That means you do not need to put a positive. I just like putting it there so they know, we know what we're talking about. 30 plus cos squared x minus 1, all divided by 2. There we go. And now, this should ring a bell. This is special angles. And remember, when it comes to special angles, there are 2 triangles that you need to remember. And whenever you see those angles, just know that it's going to be special angles. So it's always, this is going to be within a 90 degree. The one is going to be when you have it as 45 and 45. So this is actually in an isosceles triangle. That's usually because these bases are the same. The angles are the same. So the side is 1, 1. If you're going to deal with Pythagoras, you'll see that you eventually get this answer, but this is going to give you square root 2. And then this one over here is going to be for a 30 degree and 60 degree. That is, of course, 60 plus 30 is also equal to 90. And we know all triangles need to add up to 180 degrees. So that's why we know those are the 2 angles. There's another way, of course, showing how to get to this. But I'm just going to show you this in the meantime, just to save some time. This is going to be square root 3. This is going to be 1, and this is 2. Oh, sorry. I wrote it differently over here. So let's just erase. All right. So this is going to be 1. This is 2. And then square root 3. All right. So we should have it like this. All right. Okay. See someone with the answers over there. Perfect, perfect, perfect. Now, sine of 30. What is that? So sine is opposite over hypotenuse. So what is the opposite? It is going to be our 1. And what is our hypotenuse? That is 2. So therefore, this is equal to a positive of plus our cos squared x minus 1 all divided by 2. Okay, now that we have it like this, we can think about it as this is going to be, these are similar. This and this can be put together right now. So now we say negative 1, right? Negative 1 plus a half is going to be negative a half. So that's going to be equal to cos squared x minus a half all divided by 2. But now instead of writing it like this, we can actually rearrange it and write it like this. So even on C, we I got that, but I'm rather going to change it up. And you see, if we have it all like this, and if we say divided by 2, it means the exact same thing as the top one over here. Right? So it should be like that. So because we have it like this, we can now say these 2 terms can then be made together. So that is going to be placed over here. Remember, this is going to be over 1. So I told you whenever we're going to add or subtract any fractions, you are going to multiply bottom two together, and then the numerator of the one, the denominator of the one will be multiplied by the numerator of the other one, and the denominator of the other one multiplied by the numerator of the other one. So this is what they're going to be left with. 2 times cos squared x is going to be 2 cos squared x, and that's going to be that over there. And then 1 times -1, that's still going to be -1. And then 2 multiplied by 1 is going to be 2. Right, so that is this. And that is going to be divided by 2. But whenever you're going to now take a fraction and you divide, by now we all know that we can then just swap it around. So we know 2 on its own is usually just written as 2 over 1. So therefore we swap it and we say that's going to be like this. Now, when you multiply two fractions, you don't have to worry about the denominators like that. All you just do is you multiply across. So in that particular case, this is going to be, the numerator is going to stay the exact same because it is being multiplied by 1. So that's 2 cos squared x minus 1. Right? And then this is going to be over 4. Right? So we're going to have that over here. Wait, sorry, I just wrote that a bit too fast. So that comes away. All right, so we'll have that over there. So this actually comes away. This actually becomes our compound angle. So right, this is actually our compound angle over here. So instead of writing it out like this, you can then write it now as, remember, like I showed you the compound angles earlier, so it's actually cos 2x over 2. And that is now going to be, that is multiplied. Yeah, and then that is multiplied by our half, and now multiply over, because this was our compound angles that we had over here, our cos squared x minus 1, this cos squared x minus 1 is our compound angle. Then we replace it by it, then we multiply over, and then your answer is going to be cos 2x over 4. And that's your final answer. There we go. Right? And there we go. So don't forget the compound angles. Yes. So that's how it is. Cos 2x over 4. Perfect. So, okay, that was 5.3.1. Next, moving on to 5.3.2. Yes, over, yeah, 5.3.2. Now that we've done 5.3.1, normally when they say hence, we could use of the answers we got for the previous question in this question. So here they say hence, determine the general solution of this over here. Now, instead of looking at all of this, and whenever you see these big fractions, some people's like, whoa, that's too much, and I have to do all this calculation. You don't have to do all those calculations anymore. Why? Because we literally just done it now. We said that all of this is this. So we can replace it with that. So it's going to be like this. Right? So now instead of writing all of that again, you can basically just say that cos 2x over 4 is equal to your 1 divided by 25, which you got over here. Right? Now that's not the final answer. I mean, this is with 5 marks. They want us to deal with the general solution of this. Right? So this is how we have it over here. Now, okay, what we're going to try and do is we are going to try and get this cos on its own, because we eventually want to work out the general solution, and then we're going to have to deal with the cos when we're going to take the cos over and everything like that. So we're going to deal with cos. So instead of, what we're going to do is we are going to get cos on its own. So we multiply both sides by 4. That will cancel. That will cancel. This will be multiplied over as over 25. So therefore, this is going to be your cos 2x is equal to 4 over 25, right? Now that we have it like this, now this is the part where you're going to have to find your reflex angle, right? Reflex angle. That's just shorthand for angle over here. Now, if you forgot how to do reflex angle, this is how it goes. So your reflex angle is going to be, now when you take the cos, and you're going to go and bring it over, right? So you're going to go about it that way. So that's why I wanted the cos on our own. So you're going to say cos like this with what you have. So it is 4 over 25. And that's going to be equal to 80 80.79. This is the angle, so it's degrees. Now, if we look, 80.79 degrees, where do we find that? Well, that is going to be in, that's basically our angle. Sorry, that's our reflex angle. But we are not speaking of cos. So we want to say, where is cos positive? Well, cos is positive in, if you have the cos diagram, cos is positive in the fourth quadrant and in the first quadrant. The formulas when we normally follow is, when it's A, there's nothing within that in the first quadrant. You don't have to worry about the formula. But when it comes to your cos diagram, by cos, it is 360 minus theta. So we are going to be placing this angle into there, right? And seeing how it figures into that particular section. So first thing we do, let's erase everything from the slide. First thing we're going to do is, we are going to write down what this looks like within quadrant 1, which we said cos is positive in 2 quadrants. So it's in quad 1, so I'll just make it like that. That's going to be with our usual formula that we have over here. So it's this one over here. Our cos, when it was 2x, and this was equal to, so when we took our cos over, and then this was just left with this, 2x is equal to this, right? So we're going to now carry on, and now we're going to say 2x is equal to our 80.79 plus, and you normally write this over here, so that is going to be our 360 multiplied by our k, and k is the element of an integer over there, right? So that's that over here. But we have it as 2x. So what we need to do is, we need to get x on its own. So you divide this by 2, you divide this by 2, and you divide this by 2. So if that's the case, we now have it as x is equal to 80 divided by 80.79 divided by 2 is equal to 40.40, plus that 80 also needs to change, that 360. So 360 becomes 180 times k, and k is an element of integers over there. That was quad 1. When it comes to quad 2, sorry, quad 4, because that's also where it's positive, we deal with the same formula, didn't change, so that's going to be 2x. But this is, when we say this 360 minus theta, so we're going to write it as 360 minus our angle that we had, and the angle is 80.79, and then this plus 360 times k, and k is the element of an integers over there. So we have it like this. We do the exact same. We now divide everything by 2, this by 2, this by 2, this by 2, and this by 2. But not to get confused, rather first do this as a sum on its own. So say 360 minus 80.79, and then you divide that answer by 2, right? So rather do it that way. So in that particular case, you'll get your answer as x is equal to, when you say 360 divided by, let's just type it in just to be sure, 360 minus 80.79, that is equal to 279.21. And when you divide that by 2, yes, it's going to give you an answer of 139.61, because you round off to 2 decimal places. And the other thing is going to be 360 divided by 2 is 180. Okay, and k element of yes. And there we go. That's in its general formula. Did I go too fast? Did I go too slow? Did I go okay space? Is everyone okay? If not, understand. Okay. There we go. So that was our 5.3.2 worth 5 marks. All right. Now we'll move on to the next one. Yes, question 6. Aha. Now we come to trig graphs, or trigonometric graphs, or trigonometric functions, depending on how sophisticated you want to be. But here we go. In this particular case, it says, in the diagram, the graphs of f of x is equal to cos x plus a and g of x is equal to sine 2x are drawn for the interval x, the element of is equal to negative 180 degrees to 180 degrees also included. The graphs intersect at n, which is point n, where the x value of 75 degrees, negative 75, a y value of k, and then p as coordinates given over there, q coordinates given over there. P is also the turning point of both graphs. So, okay, we know it intersects as places, and we know it is the turning points. Here we go. Write down the period of f, write down the amplitude of g. Both of these are worth 1 mark. Everyone, please give me that answer. Just 1 mark. Quick, quick, quick. Easy, easy, easy. The answer is on the graph already, so it should be nice and easy. This, I'll give you 30 seconds to answer. Or at least make it 1 minute, because it's both of these together. So 1 minute, let's answer. You just have to say, maybe say P is equal to, and then you say whatever, and then A is equal to, you say whatever, because P will be for the period, A will be for your amplitude. I just want to see to make sure you guys do have your background information and background knowledge of trig graphs. So let's try it quickly, giving you 1 minute. So, okay, here we go, guys. So moving back on, I see there's people that has answered as well. I'm really glad you guys are still interacting and trying things out. There is some 180s, there is some negative 180s to 180, and some people say 360 degrees. I think I do need to explain this quickly again to everyone. Remember, when it comes to graphs, there are different things that we have to remember. The period, what they are asking for is actually how long it takes for the graph to complete one full cycle before it do the exact same shape again. So if we are looking at this graph F over here, right, it's going to be this one. So it's this line over here. So if we follow along, it starts here by negative 180. It goes all the way like this, like this, like this, until it gets to 180. And I see this. You guys have written negative 180 to 180. So I understand where you're coming from, but unfortunately, that's not the right answer. When it comes to the period, you just need to say the amount of degrees that it takes to complete that entire cycle. So the answer that I was actually looking for was the period is 360 degrees. The part where you would actually write the answer of if it is 180 degrees or like negative 180 degrees to 180 degrees, that is actually your domain. That is the part that always shows all your x values, right, of your entire graph that is needed. If they actually ask you for the range, that is all your y values. In this particular case, it would have been 1 and negative 1. So then you'll write it as negative 1 and 1. And I don't mind doing this as well because I want you guys to get as much marks when you get to the test at the end. So that is what we have so far. It's the domain. I covered the period. So the period is over here. I'll just say just P because I said everyone can also just answer this P right now. But the period is, remember how much degrees it took for it to complete a full cycle. So the answer is 360. When they ask domain, we write it like that. Range, we write it like this, which are all the y values. And then we have the amplitude. Here they are looking for the amplitude of G. Now, when it comes to that, we can erase this. So I think everyone should have that by now. When it comes to G, G is this graph. Let's change the color so we know it was a different one. Oh, sorry. This one. So G is this one. Speaking of this graph, when it gets to G, you go look at your midpoint of the line. So basically the middle part. And then from there, you go look at what's its highest value and its lowest value. Now, the way you could do this is you can just look at, okay, where's the middle between G? This is the highest point. This is the lowest point. Where's this middle point? So this one over here by 0. So now where's is the highest point? 1. So the amplitude is equal to 1. But remember, another way you can do it is you can look at the value that's written in front over here. This is G of X. Okay, it's not writing. This is a value there next to my sign. I don't know if you can see it on top of the slide there. So there's no number, so we know that's 1. Another way they can think of it when looking for your midpoint line, if you're not sure where this line is, maybe they started the graph somewhere else. All you do is you take your max number minus your minimum number, you divide it by 2. That will give you your minimum, your midline. And then from there, you look how high up it goes, right? So in this particular case, it would be a 1, and then you have it over there, and you get it to 0. And then eventually you'll see that's how it goes up, right? So a way that people normally write it is you write it as y max minus your y min divided by 2. In this particular case, it was 1 minus negative 1 divided by 2. And look, that answer is equal to 1. So there we see, hey, that is our amplitude. Okay, now moving on. Write down the value of A. So where is A? Here is A. So we see A is here in our f of x graph, which is written as cos x plus A. Right, so that is going to be by our 6.3. So in order for us to answer this, we need to find a point on this graph, right? Because as soon as we have a point, we'll be able to answer this correctly. All right, so I want to find out what is that A. So let's say, for instance, just an example. All right, so if we add, so this is not the answer. I just want to show you, for example, if you have y is equal to 2x plus c, and then let's say as a made up number, let's say we have 3 and 6. This is the x value, this is a y value. You plug in it into this equation over here, so that is 6 is equal to 2 Multiply by 3 plus c. Then you're going to say that is 6. And then this, of course, together is going to be 6. So then 6, bringing it over, it will be minus 6 is equal to c. Therefore, c is equal to 0. And that's how we eventually got what c is on its own. So what we want to do now is we want to find out what is a on its own. So that's why I'm saying find a point, right? Almost like when the people tell you, just get to the point. We're going to try and get to the point right now, right? So let's go and get it all in on slide. Okay, so is there any points on this graph that we know? Well, they told us that P over here, come on, right? P over here is a turning point on both graphs. What is P? Well, P is 45 and 1. So we write P down. P is 45 degrees and 1. So that's what we have. So, okay, they are speaking about A, so we're going to use our f of x is equal to cos of x plus A. Right, so we have that. So this is our graph we have. So this is going to be our x value. This is our y value. So our y is 1 is equal to cos, in brackets, 45 plus A. And now we are going to take the cos over. So it's going to be cos of 1 is equal to 45 plus A, right? It looks like this. Then cos of 1 is always going to be 0, and that's equal to 45A, sorry, plus A. And now that therefore means A is going to equal to negative 45 degrees. And that's how we get the value of A. Right? Does everyone understand how I got to that? Did the example help where I showed you first why we're doing it, and then voila, this is how we have it. Does everyone understand? You can give a thumbs up. Okay. So that was 6.3, right? Perfect. That's 6.3. Now we're going to move on to the next one. 6.4. Calculate the value of k, which is the y coordinate of n and q. All right. So if we look over here we have k and here we have k. And remember, we see the second part within our points that we have is our y value, and k is both there. So we know they are both at the exact same point, which would actually be like over here, right? Roughly. Whoop. Yeah, it will be roughly over here, right? Just this is equal to that. Just know it's in line with each other. That's what I mean. Right? So they will make a nice straight line over there. Just like that. Okay, so now if we have it like this, right? So we know now that our f of x was equal to, initially we had our cos x plus A. So we have our x plus A. There we go. Now, we calculated this and we eventually now said that this is now going to be cos of x minus 45. Right, so this is actually what f of x is. And if you forgot where we got that, here it is. A was minus 45. So that's where we got it. Now, we know that k is on both graphs because they literally told us that k is here and k is here. So what we're now going to do is we're going to take one of these points. Let's just maybe take n, because we are speaking of n over here. So what was n? N was negative 75 degrees and k. Right? So we had it like this. So now all we're going to do is we're going to take this point and plug it into here. This is our x value. This is our y value. Our y value was just k, so that's going to be k is equal to cos. Our x value was negative 75 minus 45. Remember, I'm just plugging it into this formula here. And this is where I'm getting these values from. So that means when we're going to type this in our calculator, that will be k is equal to negative 75 minus 45 is going to be cos of negative 120. Right? So that's that over here. Now, we can't have it as cos negative number. I told you, when we have it like this, what do? We can add it. We can add 360 to it. So that will now eventually be k is equal to cos of 240. right? Degrees. So we have it like that. So now again, cosigram, CAST, 240 going to be here. It's going to be between these two, 270. Yeah. So it's going to be in quad 3. So it's going to be found in quad 3. So what is the reduction formula within that section? That is 180 plus 180 plus theta. So therefore, we need to make that align with it. So that's going to be equal to cos of 180. 180 plus how much will give us 240? Well, it's going to be 60. So, and what is cos within this section over here? Negative. So therefore, K is equal to negative cos 60. And hey, this 60 should ring a bell for you. So let's see, it's negative cos of 60. What we're going to do is we write our K equal to, we keep our negative and the negative cos of 60. So cos of 60, if we go back to the slides over here, where did I write it? I'm just going to show you the special angles. There we go. So everyone can follow along. Cos of the special angles is going to be this one over here. So adjacent, which is this one over here, and hypotenuse, which is 2. And therefore, our answer is going to be, yeah, negative 1/2. You understand how I got to that particular part? So K is equal to negative half. Special angles. Okay, so that is now 6.4 done. Now we're going to move on to 6.5. If I'm going too fast or too slow, you can tell me as well. If you have any questions, you can place in the chat as well. 6.5. Calculate the value of x if g of x plus 60 degrees is equal to f of x plus 60 degrees. And x is an element of negative 45 to 0. Now, the way this works is, here we see that we were given certain information. So now we know that our g of x initially, which is this over here, right? So we have our g of x. This is our given. They are g of x, right? So we have g of x. And that's now also what we've just calculated. And that was cos x minus 45, right? So we're actually going to write it like that rather, because instead of having it with all this 2x and everything like that, we're just showing you. We're just showing you this over here. Or at least I'll come back to it. Let's go see. So this is going to be our g of x, which is this initially. Okay, and we should have it written out like that. So there we go, f of x. Right now f of x is equal to our cos of x minus 45. Right, and we got this f of x from this over here. Right, here we go. Right, so this is our cos f of x. So we're going to solve f of x, and then we're going to get to what g of x is. Now, what this basically means is, what does I mean by that? What this means is, whenever we see a number here, it means our graph has been shifted either to the right or to the left. In order for us to know which direction the graph has been shifted, you take those brackets and you make it equal to 0. So in this particular case, let's say maybe an example. Let's say, for instance, we have x plus 60. At least it's not even just an example. We can just take that one. X plus 60 equals 0. So if we have x plus 60 equals 0, therefore x is equal to negative 60 degrees. And what that would then mean is that x has shifted 60 degrees to the left. Why? Because it was negative. So now we see, okay, this was shifted negative by 60 degrees, right? And moved to the left by 60 degrees because of the x values that's there. Now, let's take this erase. So we have it like that. Now, if we're going to try and do the same for our g of x is equal to sine 2x. So you're going to see, okay, that was something we're going to have to try and figure out. But instead of just trying to figure g of x, which is 2 sine x, that's going to be a bit too much to cover. We saw that these points does intersect at 3 different places. Right here it said it intersects at x is negative 75, 45, and this. So what we are going to see is, we are going to see if this graph moved to the left by 60 degrees to the left, that means at those points, all we have to do is we have to move those points by 60 degrees. And that's how it's going to look. So initially we have it as x is equal to negative 75, which is this one over here. We have a value where x is equal to 45, and maybe just one down here, x is equal to 165. This is going to be shifted 60 degrees, which I just showed you now, because look, the f of x is the exact same. We just made it equal to 0. So just as a recap, x plus 60, remember that is equal to 0. So therefore, x is equal to negative 60. So all we do is we take this and we say we minus it by 60. That's going to give us an answer of negative 135. So that's one value. This, so we'll say that's one value. This minus 60 is going to give us an answer of negative 15. And this minus 60 is going to give us a value of 105. So they wanted to now calculate the value of x, and it needs to be in between these, with 45 and 0 being included. This is not there because it's not in this particular section. This can't be it because it's higher. So the only value is going to be this one over here, right? When x is 15. So therefore, to write that out, we are going to say that x is the element of negative 45 and 0, which is in that particular case. And that's because this 15 can be within there, right? So negative 15 falls in this range. Okay, so that's how we have it. Now, we're moving on to 6.6. Here we go. This is a 4-mark question. And usually when people see this over here, they get a bit nervous, right? When they see things like this. But let's read what he said. Without using a calculator, determine the number of solutions, the equations from square root 2 sine 2x is equal to sine x plus cos x has in the interval x is the element of negative 90 to 1 to 90 degrees. Clearly show all working out. So here we're going to go and see how this goes. This is worth 4 marks. Once again, I've been speaking quite a bit, so I'm going to let you guys try out now just for 4 minutes, and then I'll go through and show you how we get this step by step. So everyone, please try this out as well. You don't need too much from the other slides. The main thing that I would say is let's maybe just write down your formula so you can all see it, even though it's written on the slide. So when a gx is equal to sine 2x, let's just make that as sine 2x. Right, so have it like that. X equal to sine 2x, and f of x is equal to cos of x minus 45. Right. Now this one, what I would say is try and relate what you have to what was given to you. Right, try and relate it together over there. A hint I can tell you is that here they told us, you see what is given. I'll write it out for you as well. This part that they've given us, if we write that out, square root 2 sine 2x is equal to sine x plus cos of x. If we relate that together, this part here looks very similar to our g of x. F of x looks very different to this over here. So that means we're going to have to do some changes to f of x to make it look similar, where it might have some cos and some sine values. So try and change that f of x to have at least some cos and sine values within it. And then from there, we will try and calculate this by looking back at the graph and trying to show which values of x this will be equal. So like I said, I'll give you 4 minutes. So here we go, starting now. Okay, guys, I'm feeling a bit like I'm giving you maybe too much then. You should probably know by now, but I'm here to help you out as well. You guys can carry on with what you're doing, but I'm just going to give you another hint where you're going to have to use compound angle identities. And in order to do that, basically, let's just say there, let's write it over here. So you're going to use compound angle identities. So that, for those that forgot, is going to be cos A minus B to equal to cos A, because you might not have a formula sheet close to you, times cos B plus sine A multiplied by sine B. So how can I actually relate this to what we have? I hope you were doing that as well. So let's go for it. Carry on. Okay, so now let's see what's happening over here. So if we're going to deal with it this way, I gave you a hint by saying that you must use your compound angle identities, right? So here we have this cos x minus 45. So we'll take this as our A and this as our B. You'll see it follow along with this section over here. So if that is the case, we will then say that is cos of x multiplied by cos of 45 plus our sine of x multiplied by sine of 45. Okay, now that we have it like this, what should actually ring a bell now are these two, this one and this one. Both of it has a 45 within it. And we said whenever we have a 30-degree angle, a 45-degree angle, and a 60-degree angle, those all are special angles, right? So now we can write this out. Cos of x multiplied by our special angle, which is going to be 1 over square root 2, plus our sine of x, and that's going to be multiplied by, we can just put it like this instead, also 1 over 2. All right, we have it like that. Oh yes, square root 2. Yes, there we go. Oh, square root 2. I'm thinking of the other one, but that's right. So here we have it like this. But now we are not done. This can be, these are being multiplied by each other, so that's multiplied, and that is multiplied. So this is equal to cos of x over square root 2 plus sine of x over square root 2. And that's how we got this to look kind of similar to this part over here. That's not the answer that we've given you. All we wanted to do was make it look similar. This looks very similar to this now, and the other one looks similar as well. But if you see here, in this line here, there is no square root 2 as it was given over here. In this one, it has square root 2's within it. So now we're going to see how we can actually manipulate these formulas together. So all we have to do is, I'm going to erase. So I think, wait, let me move on to the next slide. I think I have space. Yes. So we're going to have it like this instead. So now what we can then do is we take the equation that we have, like what they asked from us, which was this. And now we're going to say a square root 2 sine 2x is equal to our sine x plus our cos of x, right? That's the x over there. All right, so we have it like this. But now what you can do is to get it how we initially had it, you see in this previous one, this one does not have a square root, whereas these does. So how do we do that? Let's just divide everything by square root 2. Divide by square root 2, divide by square root 2. So if that is the case, this will cancel. So that is going to be sine 2x is equal to, now sine x over square root 2 plus our cos x over square root 2, right? Just like this. So now that we have it like that, we can actually then say our sine 2x is this what we have over here, and this sine 2x is this sine 2x, so that is g of x, and that is equal to our this part over here. And I've just shown you by using this calculation, all of this was dealing with f of x. This was dealing with f of x, and that cos x over square root 2 plus sine x over square root 2 is what we have over here. So therefore we can say that this g of x is equal to f of x. Right? So it looks like that. But now we are not done. They want to know, without using a calculator, determine the number of solutions, the equation that has over there, as in the interval of negative 90 to 90. So all we have to do now is we have to look, where does g of x equal to f of x? All right, so where does these two actually equal to each other? And now we just look at the graph over here, and we see that they join at different places. So I'm going to now take it like this. Let's take a red maybe just to make a difference. They join over here, like for this x values, they meet up. So at negative 75. So this at negative 75 at this point, as you can see, negative 75. And they also see that shares it at P. But for this particular section, where does it also meet? At this point here. But we are only looking between negative 90 and 90. So therefore we say the values they're looking for is when x is equal to negative 75 degrees and, or basically, or when x is equal to 45 degrees. And that's where we have that answer, right? So that's where we get your 4 marks. So just we basically have to see where intersected, and then we follow the intervals that they requested from us. Okay. Sorry guys, I know we normally said we're going to end at 2 o'clock, but as you can see, there's still quite a bit to do. So I'm actually just going to be speaking on as well. Remember, there are recordings that we're going to have available, so you can rewatch these videos. But also, if you want interaction and you want to know how we got answers, you're more than welcome to say as well. All right. So okay. Now moving on. I think that's all for question 6. Let's move on. Question 7. All right. So okay. So now I'm just going to go get. Now we're just going to go get question 7. Right. So I'm just going to go get my question paper quickly. Thank you. And here we go. So 7.1. 7.1.1. Let's just see we're following along correctly. Yes. So okay, over here. Here they say in the diagram, triangle ABC is drawn. AD is drawn such that AD is perpendicular to BC. And that's all given over there. 7.1.1. Use the diagram above to determine AD in terms of sine B. Right? So in terms of this. Right? So in terms of sine B, which is this part over here, that's that angle. As you can see, that is the angle over here. So they are telling us all of this. So always specify in which triangle you are working. So we are going to work in triangle ABD, right? So in triangle ABD, which is this one over here, right? This one over here, ABD. That one over there, right? So we're going to be dealing with that. So we erase. So at least everyone knows we're dealing with that. Okay. So how are we going to deal with this? So in terms of this angle, and let's say it is sine of angle B. So that means we're going to have to use sine is equal to opposite over hypotenuse, right? There's an H over there. So that means our hypotenuse is always opposite our 90 degrees. So this is our hypotenuse. Our opposite is here, opposite our angle. So what are all of these? Well, our hypotenuse is our line AB, and our opposite is going to be our line AD. So now just write that in there. So therefore, we're going to now say sine of angle B is equal to your opposite, which is your AD, is over your AB, which is your hypotenuse. Right? And now they want this in terms of AD. So do not leave your answer like this. So we leave it in terms. We need to determine AD. So there we say AD. We make it the subject of the formula. That will now be AB multiplied by sine angle B. And that's where you get your 2 marks. That's your final sign over there. Right? So had it just like this. Okay, so now we're going to move on to 7.1.2. Hence, so now we can use all those previous values. Prove that the area of triangle ABC is a half BC, and that is times AB times sine of B. So when it comes to this over here we see that, okay, we have the areas, and there's different ways to get our areas. This area we can just say here. Area is, let's specify which triangle we're working with as well. You don't want to get marked down. So the area of triangle ABC, which is our entire one, all right, is equal to our half base times your perpendicular height that we have. So in this particular case, we have a half. What is our base? Our base is from this point all the way to this point here. So that is going to be our BC multiplied by our perpendicular height. Where's our perpendicular height? That is perpendicular to this particular line that we have over here. So it's going to be this line over here. So that is going to be AD. Right, so it looks like this. So therefore, what we can now say is we know what AD is. If we go back to our previous slide, here it was said AD is equal to this times sine of B. So now we just write that out. So that is equal to a half BC multiplied by our multiplied by our B. So AD was AB times sine of B. There we go. Close the brackets. And you can see that's how we got it from there. Right? And this is what we have. So that is how we get our 1 mark. That's what we're looking for. So we'll write that as area triangle ABC. Slide back for a minute. Okay, so I think someone's saying just go back for a bit. So this over here, I think you probably mean this one that we have. So yes, this is just how we got our angle over there. All right, so I'm just going to erase this and this so you can see it a bit better. You're welcome. Okay, so this is where we got this area, where we proved it, that it actually looks like that. All right, so this is this over here. They are the same. Okay, now 7.2. Here we go to 3D angles right now. Right, so 3D shapes. 3D shapes. Now, whenever we get to these 3D shapes, what I like to do is, the first thing I like to do is break the different sections apart and then basically decide how much size in this 3D shape I have. And then also label what we have. So we have, oh, let's read the question first. In the diagram, points B, C, and D lie in the same horizontal plane. ADB, which is the angle D, basically, is equal to ACB, which is angle C, is equal to alpha. So it is this part here and this part here. That's basically your angle of elevation that you have. Then let's say CDB, which is angle D, is equal to theta, which is this one here. And DC is equal to K units. So just K units over there. And then they say BD, which is this line over here, is equal to this line over here. So if I now erase this, so you can see a bit more clearly, here you can even see it's denoted by this. That this means the exact same. All right, that's what that means. Okay, now we need to prove that AD is equal to AC. So let's do that. Like I said, I like splitting this up with one another first. So I'm going to begin on the side over here. So I'm going to have my triangle. So I'll make it like this, where I have it as A on top, B, and D. This was a 90 degree. They said this was alpha. And this is the same as our next angle, or at least our next triangle. They go that way and this way. I just make the nice line. This is 90. This is dealing with A. This is C. And this is B. The bases are the same. Both is 90. And this is alpha as well. The angles are both, angles of elevation, both the same. I know one looks a bit bigger than the other one, but that's what we have. And then we have another triangle, which is basically the floor. So we have it like this. Okay, let's bring that up again so I can see. There we go. So this is now angle B. Oh, sorry. This is point B. This is point C, and this is point D. This is theta. This side is the same as this side, and this is K. But now you might be forgiven, or at least not forgiven, because that's what most people think is 3D shapes with 3D. So it's 3 shapes. No, that's not true. This was our first shape, our second triangle, our third triangle. there is a fourth triangle. But where do we find it? It's the entire section. So from A all the way till D instead. And then from D all the way to C. And then from C all the way back to A. So see, that entire part is there as well. So let's write down what we have for that one also. So don't forget, you have all of that parts. Let's show you the color red also. So for angle, fourth one is the entire angle, entire triangle. A, D, C. Yes, this is what we have over here. Okay, that we're just going to say that's also another triangle. There's a lot of other things that we have within it, but we covered it in everything else. We broke up the different parts. So, okay, just know that there are actually 4 triangles. Now, we need to prove that AD, which is this line over here, this long one over here, that AD is equal to AC, which is this long line over here. And that's very good because that's why we showed there is 4 different triangles. So we're going to try and get those two to be equal to each other. Where does that also meet up? You'll see it's on all the other triangles that I have. So here I'm going to now say, let's choose another color. So we can make it a bit different to everything that we have so far. Like I said, always specify in which triangle you are working. What's my marker? There. So in triangle ADB, which is this one over here, ADB, this one on the left. All right, we're going to start with that one. Here we can say, how do we get to Pythagoras? Well, that is going to be dealing with, so that's just my dots to show. Okay, I'm moving on with the section. So that is AD squared, because remember, always opposite your 90 degrees where you find your hypotenuse. So AD squared is equal to our BD squared plus our AB squared. And why is that? Pythagoras. Yes. No. Okay, Pythagoras. So, okay, now we're going to see, okay, if that is the same, they told us, what did they tell us? BD is equal to BC. So that means we can replace this BD with BC. So we can then write it out now as AD squared is equal to, which they are the same. So a BD is equal to BC. So that could also be replaced as BC. BC squared plus AB squared, right? So we have it like this. So now we look at it and we see that's the exact same. Okay, so now we have it like this. Let's just check this quickly. We'll just make sure I'm going right. AD squared, AD, so this is over here. We're going to say this hypothesis, a hypotenuse, so that's going to be our R squared. And then we have our, these two together, DB and AB. DB and AB, yes, that's correct. And then the bottom one, which is saying we can replace it to make it BC, right? So now if we take the next angle, which is this one over here, this triangle. So here we say this is AC squared is equal to, that will be BAB, or at least we'll start on the other side to make it a bit better for the voila moment. So we'll have it like this. Okay, that is going to be BC. BC squared. Because remember, we're dealing with this triangle now. This one over here. So this is our one side that we have. So that's BC squared plus our AB squared. And now we see these two are the same. And these two are the exact same as the angles that we have over here. So therefore, we now can say that our AD squared, which is this, is equal to our AC squared, which is this. And that's how we can actually say that we proved that AD, which is that line on its own, is equal to AC. And that's how we got that, 2 marks. Okay, now that was our 7.2.1. Now I move on to 7.2.2. In this particular case, we need to now prove that BD is equal to K divided by 2 cos of theta. Right, so it's going to be this long part over here. So what can we see by this? Well, if we go with all of these, where do we find K? Okay, we find K inside of our fourth triangle. That's over here. So here I'll say now in triangle BDC. All right, so it's this point, and this point here. We're working in triangle. So in triangle BDC. If you want, I can draw it out for you as well so you can follow along. Here is our B, here is our D, and here is our C. Let's see that this side is equal to this side. And this was our angle theta. Now remember, this is our K over here. Now, whenever we have our K like that, just remember that we have now our two sides. We have an unknown over here. So if we have an angle, so like this over here, an angle need two known sides. How do we know these sides? Well, this line, which we just calculated, our BC is equal to the other one over here. So we know those two are the same. So we can use the cosine rule, right? So this angle is between this side and this point over here, right? This side. So in order for us to do that, we are going to now say, let's erase. Going to have it like that. We'll just take that away. Bring it back. Or that triangle looks a bit weird, but we'll carry on. We move BDC. Those are the angles that we find within it, but the sides would be the small letters. So opposite this one would be small letter C, opposite this one would be small letter D, and opposite this one would be small letter B. Here you can see what the actual values of it is. So in this particular case, we are going to try and look for BC. That's where we're going to get our K, right? We're going to have our K. Sorry, yes, we're going to deal with this part over here. So because eventually we want to deal with our BD, right? We want to prove that BD is within here, and BD is this side. So we're going to try and bring an equation in with this. So this is how it's going to work. We're going to say our D squared is equal to our B squared plus our C squared minus our 2BC cos of angle D. All right, have it like that. Now, what is D? What is side D? That is our BC. Right, you can see that is the spot over here. That's the line BC. So it's going to be BC squared. What is B? Well, B is going to be K because that is found over here. Okay. Plus, what is C? C is going to be BD squared. And that's going to be minus 2, which is our B, which is going to be also K, also K. And then this C is going to be BD. And all of that is BD. And all of that is by our cos of D. And what is our cos of D? Well, that's going to be theta, as shown over here. Those also told to us over here. Angle D is theta. So we fall in what we know, right? So we have all of that, cos of this. Okay, now we have that. Now what we're going to do is we are going to link the parts together that we can. So we will then say we have our, this was squared as well. Remember, here's our squared. So we bring our squared down. Don't forget using your squares. So we said that in our previous one, that, or at least it was also given to us. BD is equal to BC. Well, here we have BC. So that means we can change it also to BD instead. So BD squared is equal to k squared plus our BD squared minus 2k. So I'm just basically writing everything out once again. BD cos theta. Right now, let's bring our BDs across so we can actually focus on what we have. And then we're going to have to try and keep our cos on the other side. Right? So what has our BD? Well, all of this is one big term. So I'm going to leave that on my right-hand side. I'm going to bring everything else over instead. So this entire section here, I'm going to bring over. So this part over here, red. So this entire part is going to come over. All right. So we'll write that down. So that's going to be now, I can start on the far side, just give more space. So BD squared is going to be equal to, or basically is going to be minus k squared minus BD squared. And that's equal to our negative 2k, still BD, cos of theta. All right, now we have it like this. So here we have, as you can see, as a positive BD squared, here is a negative BD squared. So they can cancel from the side. So on this side, we're only left with negative k squared is equal to negative 2k BD cos theta. I have it like that. Now, in this particular side, 2k is being multiplied by the rest of our section. So what we can also do is we can try and bring it over, right? So we can try and divide by it. But what's the use of doing just that if we want to get BD on its own? And why do we want BD on its own? Here it says, prove that BD is equal to this. So instead, to get BD on its own, I am rather going to now multiply. Let's just erase that. I'm going to multiply both sides by negative 2k cos theta so that I can get BD on its own. So here we go. Let's change it maybe to purple. So all of this is now going to be divided by negative 2k cos of theta, and this as well, multiplied by negative 2k cos theta. All right, so we can have it like that. And if that's the case, this means, where's my marker now? This will cancel with this will cancel with this, and we'll have BD on its own. So we'll have it as BD is equal to our k squared minus our negative 2k cos theta. All right. Oh, sorry about that. I suppose to rather just take the negative 1 out over here. Yes, I suppose to just multiply by negative 1 here. This was multiplied by negative 1. This entire section, that would get rid of our negatives to make it easier for everywhere else. So we just take this negatives away. I thought it's going to be a bit crazy having all these negatives. Anyway, we just took our negatives away by multiplying everything out by that. Now we just have it like this. Now, what we can now say is, this is not yet done. This is equal to, if we have k squared, that actually means it's k multiplied by k all over 2k times cos of theta. One of these k's can cancel out with one of this k's. So therefore, you can say your BD is equal to k over 2k times cos of theta. There we go. Right, and that's our answer. Right, just like this. So that was 7.2.2. Now, let's go look at 7.2.3. Determine the area of triangle BCD in terms of K and a single trigonometric ratio of theta. So, okay. These type of questions I would like you guys to try out on your own as well, but unfortunately, it is a bit difficult for you to write your answers in the, like using all of these signs as well. So I'm rather just going to help you out with this instead. So in triangle BCD, so here we have BCD, where is it? Here's our B, C, and D. It's the bottom triangle again, right? So it's again this triangle, or basically triangle 4, when we named it earlier. So here we're going to write, they're wanting the area, so we say area of, always state which one you are working with, triangle B, C, D. That is going to be equal to your half. Okay, that's going to be by your base, which is DC. And then your BD, which is going to be your this perpendicular line over here. As you can see, that's over there. So that's going to be your BD, which is the opposite side, times your sine of D. Right? And that, the reason why I'm choosing that is because that is our theta, which they are saying over here as well. Right? So we have it like this. Now we fill out what we know with all of these R values. Half of K. And BD is what I just calculated in the previous question. So that was K divided by 2 cos theta. And nice thing about that is, even if you didn't get the final answer of 2 cos, I mean, K divided by 2 cos theta, at least they told you, show that. That usually means that. They won't lie to you, it usually does mean it. So there's our theta. All right, so we have all of that. So, okay, now let's see what we can do with this. We can multiply. So this can multiply inwards. So that could be a half is equal to K squared. This is also within there. So all on top of the numerator, so that's going to be sine theta all over 2 cos of theta. Right? And then if I want to go further, we can just now multiply again, in and in. So that's going to be still K squared times sine of theta all over 2 times 2 is 4. So that is 4 cos theta. Now something should look familiar to you guys. Here you'll see you have the sine over cos. So that's another identity. So there what you can say is that K squared over 4 times tan theta is basically the area of triangle BCD. Everyone understand how I got that? Right. So that's how we get it. Right? So okay, now that was 7.2.3. Okay, now we come on to geometry. All right. Geometry, this is one of the most difficult parts of the paper. And don't worry, we'll hang in there and we'll try this out together. Right here. 8.1 states, in the diagram, chords AB, which is this part over here, chords AB, BC, which goes all there, and AC, which goes from here to there, are drawing in the circle with center O, which is this over here. It's good they told us what is the center of the circle. Sometimes they do not tell you. Then if they do not tell you, please never assume that a certain point is the center of the circle. Now let's say DCE is a tangent to the circle at C. So we all reach at this point over here. It's a tangent. And we know a tangent is a line that touches a circle at one point only. Right? At one point only. Now, here they say we need to prove the theorem which states that the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment. This is angle BCE. So it's going to be this. So angle BCE is this part over here. And you must say it is equal to angle A. Now there's a lot of proofs that you have to learn and make sure you know how to do. But in this particular case, it's going to be a tan-chord theorem. As you can see, this is worth 5 marks, and most of the time, all your proofs is worth 5 marks. So make sure you cover all of them. So what they're saying is we need to basically prove this, that BCE is equal to angle A. So the first thing that I would say is I would normally present this is, I would say to construct your radius. What is your radii? From O to C, and then also from O to B. And we can do that because they told us that O is the center of the circle. And we're linking these things together. So we're going to go and we're going to make like our radius here. Because remember, whenever we have center of the circle and it reaches the end of the circumference, we know it is going to be a radius. So there we have it, right? So in this particular case, I'm now going to say, right, let my OCB, right, that particular angle, which is OCB, which is this one over here, OCB, which is this part, let's change the color so you can see it as well. That is different. So this OCB equal X, and then let OBC equal Y. So now these are different because we just made these new angles right now. Right, so now, okay, we have those two together. But now if you look at it this way, we could actually say that angle X is equal to angle Y. But now you can't just say, oh no, that's because why? Because you have this, like this two lines that you just made up right now. No, no, no. They told us we have the radius over here, and now we have this line is equal to this line because both of it is a radius. And when we deal with the radius, we know that the angle opposite that side, the side relates to the angle within it, right? So the angle opposite that side is the same as the angle opposite this side. Right, so that's why angle X is equal to angle Y. And how are you going to explain that? You normally just say it's the base of your isosceles triangles. And normally I like specifying which triangle I'm speaking about. So triangle OCB. That's the part I'm speaking about. So, okay, if that is the case, now we can say, if we have our triangle BOC, which is the main part of that triangle right now, where you see my dotted lines linking up to the center and going all the way back to C and going up again, that entire angle, or at least that entire section is going to be, if we add it to this and add it to this, it will equal to 180 degrees. And why is that? Because of sum of angles in triangle. Right, so we have it just like this, right? And that should be equal to 180 degrees. So I have it like this. So if that is the case, we can then say that if angle X and Y is the same thing, remember you always say they are equal to each other, we can change it up. So now we can say that this is equal to 180 minus 2x, right? Because it's like the same thing. And the reason why I want to do that is because it's just much more easy to write. So 180 minus 2x, and you will see now what I do with this. We need to relate something else to this. Well, here, what else are they asking from us? Here we're saying about alternate angles. They're speaking about angle A. Where do we find angle A? Angle A is found over here, and it's touching the circle, the edge of the circle. So we can say that angle A is at the circumference. Right? So that is where we have this part over here. Now, if we say we have our BOC, which is this over here, that is 2 times the angle at the circumference. And that is one of the rules that you have learned. And that rule is basically angles at center is equal to 2 times the angle at circumference. Right, now everyone is still following along. So if that is the case, right, we could also now just shorten it by saying that BOC is equal to 2 times angle A. Remember this, these two means the exact same thing. Right? These two mean the exact same thing. Now, how we're going to change this up? We can make A the subject of the formula because they want A like that. So what we could also just say is that angle A is equal to our BOC divided by 2. And where do we get that? We just made the A the subject of the formula. Now, we are not done. This BOC has a value now. This is this value. So that means this BOC is equal to our 180 minus 2x all divided by 2. And if that is the case that we have this over here, we can then say, okay, this is 180 minus this what we have over here. And that's now going to be 180. Oh, we can split it up. We can write it like this also, 180 divided by 2 minus 2x divided by 2. That means the exact same. So that is going to be 90 minus, this 2 cancel with this 2, x. So there we can say that our angle A is equal to 90 minus x. That's x over there. Righto. So we're not done. Let's take the spot. This is worth 5 marks, so it is quite a long one. So therefore, angle A is equal to 90 minus x. So far, so good. So now we can see that angle C is between the chord and the tangent, which is this over here. Right? And that's true. But there's a line between O and C. All right, so it's this particular line over here. Now, if we are going to say our OCE, which is that line that we have over here, OCE, if it actually goes all the way down from a radius, that is the extra part that we have, right? So angle OCE is what we just calculated right now, which was angle A. Remember, it's twice the angle in the center. So that's why we say OCE is equal to 90, right? And this is because we have our radius that's perpendicular to our tangent. Now, normally, when I speak of radius and tangent, I always like speaking of which ones I'm referring to. So it's my radius of OC is to the tangent of DCE. All of those are in brackets. So this is now the same as our BCE plus our angle X, that is equal to 90. So both of these mean the exact same. Now from there, we are going to say our BCE is equal to our 90 minus x. And therefore, that we have a 90 minus x, we could then therefore say that BCE is equal to angle A. Just like we had here. Both of it equal to 90 minus x. And that's how we proved that we have these two together, right? Both of it is equal to 90 minus x. Okay. Okay, now determine with reasons the size of angle P that we have, right? So that's now going to be 8.2.1. So we need to know where is P. So this is angle P over here. Sorry, it's a new question, so I read from the start. In the diagram, PQRS is a cyclic quadrilateral with RQ equal to RS multiplied by ST. And this is a tangent to the circle at S multiplied by SR. And this is produced to make N with R2, angle R2 is equal to 68. So for our angle P, right, we are going, because we are dealing with a cyclic quadrilateral, there's a few things that we can know immediately about the cyclic quadrilateral. Firstly, that the opposite angles within a cyclic quadrilateral is always equal to 180 degrees. That is supplementary to each other. And then also, we need to know that the exterior angle is equal to the opposite interior angle in a cyclic quadrilateral. So do we have any exterior angles that you can maybe see over here? Look over here. Here we have this R2. R2 is the exterior angle and it's equal to the opposite interior angle. Let's see. Hey, look at that. And what do they want us over here? What they want us to do over here? We need to determine with reasons the signs of angle P. And just like that, there we can say angle P is equal to angle R2. Why am I saying angle R2? Because this is what they refer to it as. We also saw it over here. So therefore, you say angle P is equal to 68 degrees. And remember, never forget your reasoning. So there you can say exterior angles of cyclic quad is equal to the opposite interior angles of angles a cyclic quad in a cyclic quad. Everyone still understand? Everyone still with me? Right. So see, that's nice, quick and easy to us. Okay. Now, what is 8.2.2? What is Q1? So where do we find Q1? Oh, Q1 is over here. Okay, 8.2.2. Now, this one is slightly different. So we have our part over here. Okay, so if we see where is our R2, R2 is here, right? I just want to see how we can bring this included with everything else that we have. Do you all see that we have a triangle that goes from S all the way down to Q, it goes up to R, and then from R all the way to S again. That is a triangle on its own. So we're not now speaking about the quadrilateral, we're only speaking about the triangle. So what we could say is that the sum of two of the interior angles of a triangle is equal to the exterior angle. And what is our exterior angle over there? It is 68. So therefore, we can now say that R2, angle R2, is equal to our angle Q1 plus our angle of S2, right? And like I said, that is going to be based on the angles within the triangle that we have, right? Now, what is angle R2? It's 68 degrees. And here it was stated, we have our S, our QR, and our RS, which is actually going to be the same thing. So our ST or S2 is this one over here. Now, if you look at this part over here, this angle is going to be the same as this angle. Why? Because it's the base of an isosceles triangle. So in that particular case, we have our Q1 and our S2 over there. So they're going to give us the exact same. They are basically going to give us the exact same answer because it's base of a triangle. So therefore, we can actually say that Q1 plus Q1, right? It means the same thing. We can swap it out with each other because it's a base of an isosceles triangle. You can also write that there. The base of isosceles triangles. And which triangle are you speaking of? Triangle R, S, and Q, right? So far, so good. Now, what do we have over here? Well, we have 68 degrees is equal to 2Q1. Now we get Q1 on its own. So Q1 is equal to 68 divided by 2. So right over there. And therefore, Q1 is equal to 34 degrees. And that's how we get angle of Q1. Right. Okay, not quite. I see. I'm glad you answered as well. But this is how I normally got it, right? So you can swap it around like that when you bring the two together, right? So that actually now would mean that we have another way you can check this out now. Was remember I said the sum of the interior angles would equal to the exterior angle. So 34 plus 34 would again give us 68. Right now, exterior angle. Right, yes, thank you again for answering. Okay, now 8.2.3. We need to determine S1. Now, S1, where do we find that? That is between S1 is here, over here. We find that between this section over here, which is line ST, and SR, which is this line that is within our circle and it goes out the circle. That was quite a bit over there. So let's erase what is happening on the slide. So here we see, okay, so our angle S1 is equal to our Q1. And why is that? Because we can say that is our tangent. So basically, I'll just refer to as tan. But which line is our tangent? That's our line ST, which is this one over here. Chord. That's dealing with a tan chord theorem over here. Well, where's our chord? That's this one over here. So that is SR. So I'm just specifying where we find it, just to make it like let the examiners know what we're doing as well. Theorem. So this is the tan chord theorem dealing with our ST and our SR lines. And that's how we know that these two angles is going to be the same. All right. And if that is the case, all right, so here we have this. So if we have Q1, we have dealt with Q1 already. Q1 is, like we said in the previous one, that is 34. So therefore, S1 is also equal to 34 degrees. Right? So don't forget to always write your reasoning. Okay. So that was our question 8. Now, moving on to question 9. Sorry guys, it's taking so long. It's just this is a very long question that we have over here. All right, so a very long question. Okay, now determine, or at least new question. So let's read. What I see over here, you say R of R equal to 180. Okay then. Okay. No, I see where you're coming from there, but I think you're taking it as a straight line and then you went from there. Right? I dealt with an exterior angle and then I made that our 68 and then we went further from there. Right? But now let's move on to question 9. Thank you for that. In the diagram, AB is a diameter of the circle with center F. AB and CD intersect at G. FD and FS are drawn. BA bisects CAD and D1, angle D1 is 37 degrees. That's a lot to take in. Remember, don't make that mistake of confusing bisect with intersect. Bisect means that cut the angle completely in half. So if you have two lines like this, another line come over the side, you will have, let's say maybe 32 and 32 on the side. But if you have another angle, it could cut it at a weird angle like this, where one is like way more, so maybe that is 49, and this is only 7. All right, so that is intersect, and the other one is bisect. Okay. Now, we are told various things over here. What we can see is that angle D is at the circumference, so it's on the circumference. Remember, there's various rules that we're going to have to follow when it comes to dealing with geometry. So that is on the circumference, because we could do maybe angles at the center over there. Two times the angle of circumference, but now at least we know, okay, that is angle D. We know that angle D1 is between two different chords. It's between chord D and B. And if we follow it along, it's also between D and C. All right, so that's where we get our angle D1 from. That's the angle D1 is from there. Why we're focusing on that is because they're telling us this. They want to know with like 3 other angles that is also equal to 37 degrees. So that's why I'm trying to say as much as I can get, all the information I can get from that angle by D. So if that is the case, what we can see is that by this part, we have the 2 chords that makes up angle D. So if I take this away, this chord makes up angle D over here, and this chord makes up angle D, right? So it's B and C. And then we look, is there any other angles that those 2 make up? Well, yes, there is. This line, which is B, goes all the way down, up till there. C goes all the way down till there. So that is the spot over here. So therefore, we can then say that angle D1 is equal to angle A2. And the reason for that is you can say angles subtended by same arc. You can think about it like this. This 2 between B and C made this one as well. The spot over here, right? So it can be a reasoning. And what was the 2 points that we dealt with? B and C, right? So there we go. Now, based on that, we can look at something else. So let's take a eraser so we do not get too confused by all of these lines that's on here. There was another important information that they gave us at the start, and that was here. BA bisects CAD. So where's CAD? It is this angle over here, this entire section. And I told you at the start that this will cut it into, at least I told you bisect means it cuts the angle equally into. So therefore, if we just said that angle A2 is equal to 37, then therefore angle A1 is also, they are equal together. And therefore you can say that is because it bisected it from each other. So therefore you can say angle D1 is also equal to A1. So we have 1 and 2 angles that's also equal to 37. They wanted 3, right? So 3 over here. Oh, like I said, give reasoning. So they can just say this was a given that BA bisect CAD. Right? There we go. That is your reasoning here. Always remember the want with reasoning. Okay. So far, so good. We have 2 out of 3. Do not give up like that. Make sure you can carry on and see how much further you can go. Now, if we look at something else that we have, here we can see that A2 is in this triangle, over here it's reached by the points F, A, and C. Right? Now that is going to be where we get our angle A2. So A2 is within that triangle. But if here they say is the center of your circle, so that means when you go from F till A, so line FA is the radius, right? So line FA is the radius. Now, if you look at this, what else? This is the center, and it's reaching the point over here as well, which is C, which means line FC is also the radius. Right? Now we know, okay, that is the radius and that is the radius, which means this line is equal to that line. They are both the same. And like I told you, the sides relates to the angles within it. So this angle is speaking to that angle, and this side is speaking to this angle here. We know that A2 is equal to D1 because we just proven it. And therefore, we can also now say that, so firstly, I'll now say A2 is equal to C2, and that's because it's both radii. And then you can say that is now equal to also D1, because I want to find with reasoning. So then you can use that same example because we have 2 sides that are equal. So that makes it the base angles of isosceles triangles. And then just because we want to be extra and show them you know what you're speaking about, they're speaking of triangle FAC. There we go. And that's where you got to 3. Righto. I hope you guys are doing along as well. I see someone asking, couldn't they have done congruency for 7.1? Yes, just carry along. They should actually, you should be able to do it. And you'll be able to see, yes, you have the answer as well. But yes, you should be able to do. Okay, now 9.2. Show that DG is equal to GC. So where is DG? DG is this line over here. I will circle it so we know, okay, that is speaking to that. And GC, this line, is this one here. So now we need to show that these two are equal to each other, right? Even though it's cut like that, they didn't say, okay, it's cut midpoint, or it's has bisected the lines or is perpendicular or anything. All they are saying now is we need to show that DG is equal to GC. So now, if we look at this, if we have a line drawn from the center, right? And do we have a line drawn from the center? Because whenever you have a line drawn from the center and it interacts with a chord. So a chord, remember, is when a line goes from one side of the circle all the way to the other side of the circle, but does not go through the diameter. Or, sorry, does not go through the center of the circle. If it does, it's the diameter. If it doesn't, it's called the chord. Now, in this particular case, if a line is drawn from the center and it's perpendicular to a chord, that will immediately bisect the chord. So then we know, okay, it will make those two equal to each other. So now with that rules, it's almost like you have to work in reverse now to show that this is actually happening. Now, in order for us to make that, or in order for us to do this in reverse, we need to then show that this line, FG, so new color, let's make it, now we have red, just a dark blue is fine. Let's say, so we need to show that FG is actually going to be perpendicular to DC. Reason why is because this is this part coming up here. If it hits DC, which is this point here, nice and perpendicular, we know immediately it is, then it will bisect the line and our two sides should be equal. So this is how we're going to try and deal with this particular section. Okay, so in this case, we are now going to show that we have triangle. Let's make it here. So we have a triangle. I'm going to now specify in triangle ADB. Let's speak about it in that triangle. All right, so in there. We can even try and draw it as well. As B, like this and like this. Here is our B, here is our D, and here is our A. So can you say if 2 is equal to A1 angle in same segment, U1. I'm just trying to see they are asking a question if they can maybe change it up by using D1 instead of A1. So normally if it comes to the angles in the same segment, remember it needs to be on the same side, yes. That's usually when you go from your 2 points, but it's almost like you make your arrow shape from there, right? So in order for you to make your arrow shape like that, you're going to need to go from like your center and then carry on like this, right? So rather you need to make sure that you follow along to get your arrow shape. So you have your center and then you try and moving it along to see how you get to that point. So if you try and get to 57, you can see how it works, but just make sure that you deal with your reasoning as well, right? But to me, those were the 3 that I came up with as well. You can more than welcome to try that out as well. So anyway, carrying on. So here I'm going to have this triangle. Now I'm going to say angle ADB, which is this one over here, this entire section over here, right? In triangle. So basically angle ADB, right? That's going to be equal to 90 degrees. And why do we say it's 90 degrees? Because this angle is subtended by the diameter. And which diameter are we speaking about? It is AB. Right? So this is AB here. Here's the AB, which is the part all the way in the center. So by the diameter, AB. Right? So all that is subtended by it. Because remember, whenever you have a circle, line through center, wow, I missed that completely. And then you go to here and there, this will always be 90 degrees. Right, that just goes straight through. That's the part I actually needed to get through. But anyway, that is this. So the entire part, angle D, is equal to 90. Why? Because of this reasoning. Okay, so now, dealing with the angles they had earlier, we can now say that angle A1 is going to be equal to 37 degrees. Now you're probably thinking, whoa, how did I get 37 over here? Remember, I told you, previous one, or at least one of the previous slides. Here we go. All right, let's use it as well. Right, so that's the reasoning. So no angle is 37 degrees. So if that is the case, now we can say that ADB, or yes, so now we can say that wait, sorry, I must swap these two around. So we're dealing with the last one right now because we have this over here. We know that's going to be 90. So we find out the last one, so we need this section here. Because we know this is going to be 90, and then we can find out what is our last one over here. So angle ABD, there we go, is equal to 180 minus 90, because we spoke about it here, minus 37, because we spoke about it here. And that's going to give us a value of 53 degrees. So this value is 53. Right, so that is 53. Now we go and look in triangle. Remember, we specify now in triangle BDG, which is this one over here now, which is on the other side. This small one over here, right? This one. So now we know there is a 53 and a 37. So now we're going to see what else we have. So in this shape over here, we can now say that the leftover angle that we are speaking about is DGB. There we go. And that is now going to be equal to 180. I just skipped the first line because we know DGB plus 53 plus 37 is going to be equal to 180. So I'm just writing this out now. So we're going to have it as 180, because remember, sums of triangle. So 180 minus 37, which was our D1, minus our 53, which is our B. That is now going to all be equal to, that's now going to be equal to 90 degrees. There we go. That should be 90, because we're looking at this last one over here. And that is the angle we were looking for. Now, because this is 90, that means, remember, we said that this was bisected. So, right, we see this is 90. The line came through the center. And because it's at 90, therefore, automatically, we will now know that DG is equal to GC. And why? Because the line from center is perpendicular to chord, and when it bisects chord. And which lines are these? If you want to be extra, just know that this line is FG. Yes, in the center, FG, which was this part here, this middle piece, from the center up. And this chord over here was DC, the lines we broke into two. So, okay, that is how we're done 9.2. I know it's quite a long one, guys, but yes, usually geometry does take a lot to go through and stuff, and I really want to make sure everyone do understand where we're getting this. And as you can see, there's a lot of rules for you to remember and follow along. But that is how we get this. Now, moving on to 9.3. So I'm just going to take a sip of water. I'm sorry, guys. Just 9.3. In the meantime, everyone can read what is that over there. I'm just going to take a sip of water quickly. Okay, sorry about that, guys. Just needed to figure something with it. Was quite a bit of talking. But anyway, moving on to here, it is said all the top parts are the same, 9.3 states. It is further given that the radius of the circle is 20 units. Calculate the length of BG. So BG is this here. We're going to calculate that. And they're saying the radius is 20 units. Well, where is the radius? Well, we know this is the radius, so that will have 20. That is FC. We know that DF, where's this marker? The DF is also a radius. And we know that is because there's 20 units over there. So let's move on and see what we have. They want to speak of the length of BG. So let's put a section that we have over here. So if we have FG plus our BG, that's the G over there, that is actually going to also be the radius. And how do we know that? Well, it went from the center of the circle, it went up. It didn't now start turning and go that way and then up and then somehow got to the section over here. No, it went straight up. Unlike my arrows, but they went straight up over there. So that's why we can say FG plus BG is equal to your radius. Therefore, that means that is also equal to 20 units. Right? Just like it was stated here. Okay, so now let's take all this other stuff away. Don't erase everything. Okay, so let's see how it looks. So now we can see, okay, what do we have? So that means this is a radius, which is a base. This is a radius. And then we can then see that this entire part, so this is also a radius here, right? So this is the radius, where I just said it's equal to the radius. So if that is the case, right, we have various radius that comes over here, another one over here, right? This part here. There we go. So in this case, if that is it, if we look at triangle, in triangle DFA, this and this. This part points to this section, this part points to this section. Therefore, we can then state that D3, or angle D3, is equal to angle A1, because we have it like that. And because that is the case, we also know, same reasoning, to have, let's just erase this quickly. Same reasoning. We bring this up. This over here, that represents this entire section, right? So that angle that we have over here, that's going to now be equal to our D1, equal to angle D1, right? And why is this? Base of angles in isosceles. Isosceles triangles. Which triangle is that? ADF, right? ADF. Now that's how we're going to go over there. So, okay, that's how we can state all of this looks right. So, okay, now what we can now state is that angle D1 plus angle D2 plus angle D3 is all going to equal to 90 degrees. And why is that? Remember, we said that because of this line that all meets up at that point over here. It covers all of that. So if that is the case, we can now state that this is going to be all of these three that we have over here. This, and this is all going to be equal to 37 degrees. So now we replace everything that we know over here. We said D3, A1, and D1. A1 is not in here. So that is 37 degrees plus our D2 plus our D3. D3, let's take this away. So D3 is also this part over here. Remember, 20 is just the radius. We're looking at the angle. So that is also 37. G equal to 90. We make D2 the subject of the formula. So that is 90 minus 37 minus 37. And that's going to be equal to, so angle D2 is equal to 16 degrees. So that's how we now know what this full 90 is, right? So that's how I make up the 90, because we have it like this. Okay, so that is angle D2, which is this middle one over here. Now I need to go to the next slide, because I need more space. So, okay, so angle D2 is 16 degrees, righto. And that's the triangle that we have. So what we're going to do now is, okay, so if we write this out, just with what we have, D, I'll just make it like this, so I can picture it a bit better. D, F, and here's G. So we're just dealing with this triangle here, here, and here. So at point D is D2, and D2 is 16 degrees. We know that this was the radius, and this is the radius as well, right? And this point over here, right? So we know those two as well. So if that's the case, we know that these points are now going to be equal to the same. So now we're going to have FG, right? We're going to try and calculate this here. Sorry, the radius, the entire path, the entire section over here. So we're going to try and calculate FG. So in order to deal with what we have here, we are now going to show that, okay, this is 16. We said this is 90, because remember we have 90 here, 90 here, 90 here, 90 here, was perpendicular bisector. So at point G, so these two are actually supposed to swap. Erase this one and this one. This one comes back. This is G, and this is F. This was a 90 degree here. And then this is what we're trying to calculate. Let's just make that theta. So because we have it like that, we can decide everything else that we need. So in this particular case, we can just now say our FG is equal to our DF times our sine of 16 degrees, right? So I have that over here. Now applying the values that we know that FD is 20 units. So we say 20 multiplied by 16 sine of 16, and therefore that's going to be 5.51 units. Now, very importantly, when you get to this section here, please make sure, so I'll even write there, make sure your calculator is in degrees. And then you will get this answer. So when you get to the spot, please make sure. Now, we're going to take our BG, which is going to be this line over here. Remember the rest of it. That's basically now just going to be our radius, which is the total amount of it, minus our FG, which you just calculated over here. So that is 20 minus 5.51. Type that in your calculator, and you're going to get your answer of 14.49 units. Because you see the radius was measured in units, we're just going to use units as well. And that is going to be how we do 9.3 with 4 marks. Right? Just like that. Okay. Okay, now, yes, so this looks about perfect. Now, we're going to move on to next question. Just the same that I have here. Question 10, last question. Okay, now I know this was a lot to take in, but here we go. We're on the last one right now. So, in the diagram, COD is the diameter of the circle with center O. Right, so that's over there. EA is a tangent to the circle at F, and that is AO is perpendicular to CE. The diameter of COD produced intersects with the tangent to the circle at E. That is OB. OB produced intersects with tangent to the circle at A. CF intersects OB in T, CB, BD, OF, and FD are drawn. They have that over there. We need to prove with reasons that TODF is a cyclic quadrilateral. Now again, as a recap, whenever you see the word cyclic quadrilateral, two things need to come to mind. It has two features that you can think about it whenever it comes to that. Basically, that the opposite angles are supplementary. Meaning the angles add up to 180 degrees. Right? So basically angles equal 180. Can think about it that way. And that's the angle, not C. Angle. Next one. When it comes to cyclic quadrilateral, the other one is for exterior angles. We have covered this early in this lesson. Exterior angles is equal to the opposite interior angles of those angles. Right? So if we manage to get certain parts of this, like if we manage to get two opposite angles equal to 180, then we know, we're on the right track. Then we can see this is a cyclic quadrilateral. And remember, that's usually when 4 points is touching the circle, right? The edge of the circle. But we're going to see if this works now. When they see cyclic quadrilateral, this should come to your mind immediately. So, okay, now we are going to look at, they want to know if TODF. So where do we find TODF? T is here. So is this point over here? T, O, D. Well, that is D, and that's F here. They want to know that those four pieces actually does make a cyclic quadrilateral. Right. What we can do is we can now see that we state which one you're going to begin with. So in triangle CDF, which is this outer part here, C. Let me change the color. So in triangle C, D, and F, those big ones over there, right? If you look at what was given over here, and also in the information that we have, you will see that our, I'm going to take erase so I can follow along. I'm going to bring this part back. Okay. So we're speaking of this point, and this point. Now, there are these that make up that point C within that triangle. Within this triangle, we see that, oh, sorry, not this triangle, at that point in the angle is this, and this point in the angle, that is going to be DEF, yes, so this part over here. So as it comes up, it could go here and this, so it's this entire section over here. Righto. So therefore, in triangle CDF, we can say that our F2, which is this one over here, plus our F3 is going to be equal to our, which is the entire part, like I said, this entire section here, right? So in that particular triangle, F2 and F3 is CFD. So we have that, because remember, that angle is within here as well. Now, if that is the case, we have it like this. Yeah, it was saying that this was bisected. All right, so see, I mean, sorry, it is like this as well. It's perpendicular. So therefore, we can now say that our CFD is equal to 90 degrees. Another way you can think about this is that this is angles in a semicircle. Right, that's going to be, here's our center, angles in the semicircle. There's another reason that you could think about, and you could write it as the angles at the center is 2 times the angle at the circumference. So if that is the case, that then means O1, which was this, and you can see it as the 90 degrees. Therefore, O1, angle O1 is equal to 90 degrees, right? Because that was at the center. So now because we have it like that, we can see that those two are those two points are opposites from each other, TODF. So because those two are opposites from each other, we can then say, therefore, TODF is cyclic quadrilateral. Ooh, quadrilateral. Okay. I have to make sure I spelled it right. It's been a long day, but we have this over here. And now you can show that this is your angle that you have within this triangle C, D, and F. You can then also say that is because of exterior angles is equal to the opposites of interior angles. This is follows along with this over here. So because we know what this is, we said TODF. So it's going to be TODF, and this is the angles outside, and that's where you can get your reasoning. Okay, so we've understood that one as well. Good. Now we move on to 10.2. Prove with reasons that D3 or angle D3 is equal to angle T1. So in this particular case, let's look. Okay, there we go. We need to prove that D3, which is what we find over here, D3 here, is equal to T1, which is this over here. So, okay, there's various ways that we can think about this over here. But now, if we look at what was given, this is on the line of OA. That goes all the way out of the circle, all right? And then we have another one that lines over there. We have this particular section here that cuts it, right, as it's moving along. So let's see, where does it actually go? This cuts that particular section, which is line CF, right? So line CF. So I'm just saying that this, you have a certain part, and here you can cut it across. So this can be like CF, and this is like OA. Those are what we have over there, right? Now, if we look at only OA, the line that is the spot over here, line OA, that would then mean that T1, right, T1 plus T4 will be equal to 180 degrees. Now, the reason why I'm using this O and the C and F is because here we also speak about the CF here, right? CF. And here it intersects OB at that particular case, right? This is also at our COD, where it is this particular section. When it cuts it like this, when lines intersect like that, we have the vertically opposites, where these two angles will be equal to each other, and these two angles will be equal to each other. So let's make, we say this is X, and this is Y. Then vertically opposites, so this would be Y, and that would be X, right? So if that's the case, if we're looking at this T section only, we can then say that T3 plus T4 is also equal to 180 degrees. And if that is the case, we can say T1 is equal to T3. And that is vertically opposite angles. Vertically opposite angles, right? Yeah, you can see in the diagram here was T1 and here was T3, right? So vertically opposite angles, that's why they would be equal to each other, right? At that particular section that we have. So now that we have it as this particular part, because they are cutting each other like this, now we can then say D3, because they want to know how D3 is looking. We can then say D3 is equal to angle T3. And why is that? Because this is the cyclic quadrilateral, which was proven in the previous one, where we deal with TODF. The exterior angle of your cyclic quad is equal to your opposite interior angles. So this is our exterior angle, and our opposite interior angle is this T3. So therefore, you can then say your exterior angles of cyclic quad is equal to the opposite interior. The double P, you're going to write the whole thing out, but opposite interior angles. Angles. There we go. And therefore, because we said that T1 and T3 are the same, they want to know that this is that. So then you can just say angle D3 is equal to angle T1. And that's where you get that mark. Okay, that was 10.2. Almost done, guys. 3 more questions. So, moving on to 10.3. Proof with reasons that 10.3, triangle TFO is similar to angle or to similar triangle DFE, which is worth 5 marks. Now, whenever you see these 3 lines, remember this is similar. When it's 3 lines like that, congruent, right? But these are similar. And because we're speaking of similar, there are things that has to be known. There are 2 things when it comes to similar triangles. The sides are going to be proportional to each other. So 6, 9, 12. And that's how I can see if you double one side of the angle and it equates to the following one that you make bigger or smaller, that's going to be similar. And basically all angles must be corresponding with each other. Okay. Now, proof with reasons that we have this, that these 2 are interacting with each other. So in our previous one, we just calculated that D3 is equal to T3, right? These 2 angles are equal to each other. But we were told a lot of information over here on top. And here we can also see that our OF, which is this line over here, where is my marker? Yeah, OF. So from this point, OF is going from the center to the edge. So you can say the OF is equal to my OC, because it goes from here as well all the way to the edge of the circle. Now that's going to be also OC. And why is that? These 2 are together because of radii. There's both radius, right? Both are radius. That's why you don't say 2 radius, you say radii. So, okay. Now, we want to speak of this one. So we're trying to get to triangle TFO. But now the first thing we need to know is we're going to see what we can deal with this OF and OC. So if we deal with OF and OC, let's try and make a triangle out of that. So if we have 2 sides, that is a radius. So that's going to be this one and this one. That will then automatically mean that triangle CFO is an isosceles triangle. And by now you already know where we always go with these isosceles triangle stuff, with the bases. That's going to be the same. So if that is the case, this entire angle, this is pointing to our C2, and this is pointing to our F1, right? Sorry, F2. So therefore, we are going to say that our angle C2 is equal to angle F2. Why? Because base angles of isosceles triangle. Remember, guys, there's a lot of different ways to get to your answers. As you can see, one of my favorite ways is look at my radii, see if I can find bases of it, and then I always go with that. Right? This just always works out for me anyway. So, at least most of the time. So in this particular case here, I like dealing with my isosceles triangles. So we'll have it just like this. So if that is the case now we can look at our triangle, our angle E, which is all the way on this side of here. What does this have? Well, if you look at the bottom triangle now, DFO, which is another color, DFO, this, and this, right? So angle E would actually be equal to the sum of the angles of a triangle, right? Because we know that is now going to be equal to 180. So if that's the particular case, we can then say E is equal to our O2. So it's this part over here, so O2, because these are our angles that we have. I'm sorry, I think I just jumped over there for a bit. Yeah, I was like, that's a big leap to take. Okay. Right now. So now we go for, yes, there we go. That makes more sense. So now we're going to look at our B4, which is this one over here. So our F4, which is this, and that's going to be equal to our C2. And C2 is this side. And why are they going to be equal? And that's because of the tan chord theorem. This line, EF, let's take all this away, so I can actually see what's happening here. This line, EF, is touching it at one point, so it's our tangent. And this is our chord that goes all the way up, which is this over here, right? Our chords, that's over there. So in that particular case, we can then say our F4 is equal to our C2, and that's because of the tangent, which line of EA, and with our chord, which chord? EF theorem. So if that is the case, we can then now say F4 is equal to F2. Right? So it look like that. And because those are now equal to each other, we can then say E, which is the one on the outside, is going to be equal to our O2, which is on the inside. So therefore our E is equal to our O2. And why do we know that? Because sum of angles, a triangle, equal 180 degrees. Right now. And now remember, we want to show that these are similar to each other. And what did we use? We used the version of angle, angle, angle. Right, and that's how I can show those are similar to each other. Now, 10.4. If B2, angle B2, is equal to angle E, prove that DB is now to E, right? So that's going to be now parallel to E. So, okay, whenever we see parallel lines, that should bring fun to your mind, because when it comes to parallel, there is 3 different cases as it could be. It could be F, U, and N, right? Where the corresponding angles, here your co-interior angles, and here your alternating angles. Corresponding angles is this one up here, right? And their co-interior angles are the other one. So that's what's going to be over here. Now they're saying if B2 is equal to E. So we write that down. They're giving us information. If B2 is equal to E, right? Then we can say in triangle OBD, which is this one over here, O, B, and D, the entire section, we can see with that we have radius or radii. This is a radii. This is a radii. As hitting the edge of the circle. So therefore we can say that OB, so I'm underlining that. So OB is equal to OD. Why? Because it's radii. So now because both of it is radii, speaking of that triangle, here is our B2, because this is now the angle opposite this, which means the angle opposite this one is going to be D1. So there we can say B2, or angle B2, is equal to D1. And then my favorite reasoning by now, hopefully yours as well, base of angles of your isosceles triangle, which is OPD that I'm speaking about right now. So we have that over here. So that is what this one is about. Okay, and then we see, okay, that is this entire triangle that we're speaking about here. And they're saying that B2 is equal to E, which is this part over here. All right. So because we just said that B2 is equal to D1, that would then also mean that D1 is equal to E, because that's what they told us here. Right? And what that would now mean is we can then have a corresponding angle when it comes to that particular part here. It will then go like this. So let's take erasers. And go so across and down and come back up, right? So we can go like that, and like that. So then you're going to state that DB perpendicular to EA, and that is because of your corresponding angles. And that's side 10.4, right? Okay, moving on to the last one, right? The last one. Here we go. And this one is worth 5 marks. That's another proof, right? So in this particular case, we need to prove with reasons that our DO, so this line over here, DO, all the way over here, is equal to TO, which is the small part, FE, which is F and E, which is this part here, and AB, which is this part over here. And divided by AB is actually the same thing. Not just throwing lines and stuff like that over there does not actually help us with the answer. So instead, what we can do is we want to know. Now tell us clearly. This is what. Here's my marker. It's okay. Now we can say that in triangle ODB, right? So we're going to have this entire section over here. If we have that triangle, what size do we have that is needed? D and O, right? If we deal with triangle D, F, and E, what is needed? Let's not put a divide, otherwise you might think I'm busy dividing all of these by each other. So let's write that. So within there, this is what we find. Within this, we find our F and E. And within this particular one, in triangle TFO, what will we find? T and O. And that's how we're going to now try and speak about our TO, our FE, and our AB. Now you might think, hey, why did I forget AB? No, no, no. We're going to get back to that. We're proving that DO can relate to that. Because remember, there was no A in any of this. So I needed to find another way. So we have 3 of these at least. Right though. Now, the way we deal with this is, let's say, for instance, we have a rectangle, right? Rectangle can maybe look like this, of course. So long this way, that way. We have A, B, D, and F. That would then mean that your A and D line will be parallel to your AB line. Remember, they're going to come like this. Sorry, your AD parallel is when they don't touch, so not perpendicular. So let's change that up. Right, so this can be like when you have your AD, and it will be parallel to your BE, right? The A1 touch over there, right? They're parallel to each other. Now, when it comes to triangles, it's slightly different. Let's say, for instance, we have a triangle. Change the color so you know, so we can have something different. So if you have a triangle, let's name it A, B, C. Then we make a midpoint line between those two, these two lines will be parallel with each other. So that is now D and E. If I have it like this, then that would then mean our DE is going to be parallel with BC. Right, so that's just how we can see now, depending on the shapes that we have, if it's a four-sided shape or three-sided shape. Now we can see if it has parallel lines as well. Okay, so now we come on to the next slide. So, okay, if that is the case, and this is how we're going to run it, we can then actually say that these three angles, our A, if we look closely, it carries on O and E, right? So that's over there, A, O, E, and E, right? And then I'll choose another color over here. Let's go color. Let's say A, B, and they can actually make another point. They can go nicely to C, right? So just have this path goes up like that, right? But now that would be weird. Just have those two that is relating to each other like this, right? Instead, what I would then say is, let's rather take this out. This is actually A, F, C. So this goes together. So, right? That's why we have that over here. Now, when we mix all of those together, you'll actually see that they are congruent with each other. Sorry, they are similar to each other because of how big it gets and how small it gets. So what does all of these things actually share in common with what I had over here with these three triangles that I was speaking of? All of it actually does, if you see ODB, which was OD and B, it links up with A. If you see DFE, DF and E, eventually links up with A. Anything else? Yes, triangle TFO, TF and O eventually links up with A. So all of it does link up with A, right? They share a point of A. So there you can say they share point A, and that basically means that the lines are proportional. Okay, so in that particular case, we can then say that our triangle ODB is like this with triangle OEA. And why? That is because of the lines DB is parallel to EA. DB, which is this part over here, DB is parallel to EA. Right, so we know, okay, they are parallel with each other. They will never touch. So if that is the case, we can now say that OD is over DE, which now remember we can do proportionality theorem, which we have learned in grade 12. It's the same as saying OB over BA. It's a B, and that is equal to DB over EA. Right? So it's looking like this. But since that we only need a OD from this part, or DO, OD, we need this part over here. All right? So I'm rather just going to then take these two. I'll speak about these two over here. So we can say since we have OD, that's equal to OB, we can say therefore DE is equal to BA or AB, depending on what you want to say. This is proportional. These are equal to each other. That's what this basically says here. So far, so good. We're seeing that these are lining up nicely with each other. Now, let's move on to the next slide because we're not yet done. This is now going to show us that also dealing with the proportionality theorem when dealing with these triangles that I have over here. you can then go now say that your OF over your FE is going to now be the same as a TO over DE. Once again, proportionality theorem, right? Is equal to TF over your DF. Just because we're seeing like which of these sides are now proportional to each other. Right? So in that particular case, we're now going to go look at these two. With these two actually has corresponding sides. And I must say there's always things you have to look out for when it gets to these type of triangles, right? When they're lining up like that to each other. So in that particular case, you can then say that your TO, which was this in the middle, and to my T, right? So it goes down like this. My TO, and just still there. And then we also have our DE, which goes from here to here. These are just our extra sections in order to get now to our radius, right? Both of these are radius, but going from one side to the other side, right? So we're going to have our TO, and then bring that over. This is not the exact radius, this is just like part of it that we have. So we're then going to say this line over here. This we can bring in with our radius instead. This one here, O and F that we have, and our D and the O, because that can relate better to what we have over here with our D and O and our FE over there. So in that particular case, because we say now our OF is equal to DO because of radii, you can say your DO over your FE is equal to your TO over your AB. And look at that. There you have of your ones over there, TO, FE, and AB. So now we're going to try and make this the substitute of the formula. So you're going to take your FE, and because you're dividing at the side, you're going to multiply it by the other side. So this is now becomes DO is equal to your TO FE all over AB. And then that's where you get this one from. Okay, and that was worth 5 marks. I know it's been a very, 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 very long lesson, but I just wanted to make sure we get through this entire grade 12 maths paper 2. Hopefully you won't take this long for your exams, but as I was speaking, I wanted you guys to understand also while I was answering, and then like showing you certain things to remember as well. So, but don't worry, yours will usually be 3 hours. But then it's been a long day. I really thank you guys for staying with me in this lesson, answering of the questions, asking different questions as well. But I really hope that everyone really enjoyed today's lesson. And from everyone at the Cape Town Science Centre and the people who sponsor this, which is Astron Energy, we thank you all. And please do not forget to join our tomorrow lessons, which is paper 1 and paper 2, life science. One will be in the morning, one will be in the afternoon. Right? Those are just going to be 2 hours each. But thank you again all, and all the best for your exams. Thank you.